Alright, looks like we're live. So what we're doing is we started off, let's just get this, going here. Alright. Progress meter. Really? I'm not quite sure what happened. Okay. Wait, let me just run all of this. Okay. Do we have a local manifest? Let's just yeah, I didn't do this on this computer. Oh shit. Okay. Alright. Always a million errors. Anyways, let's see if this is picking up anything.
And used an NLP to predict the next character in the sequence. So what we'd like to do now is we'd like to...
I wish I could get a playback.
Move on to more complex and larger neural networks, like recurrent neural networks and their variations like the GRU, LSTM, and so on. Now, before we do that though, we have to stick around the level of multi-level perceptron for a bit longer. And I'd like to do this because I would like us to have a very intuitive understanding of the activations in the neural net during training, and especially the gradients that are flowing backwards, and how they behave and what they look like. And this is going to be very important to understand the history of the development of these architectures, because we'll see that recurrent neural networks, while they are very expressive in that they are a universal approximator and can in principle implement all the algorithms, we'll see that they are not very easily optimizable with the first-order gradient-based techniques that we have available to us and that we use all the time. And the key to understanding why they are not optimizable easily is to understand the activations of the gradients and how they behave during training. And we'll see that a lot of the variants since recurrent neural networks have tried to improve that situation. And so that's the path we need to take, and let's get started. So the starting code for this lecture is not in the code before, but I cleaned it up a little. So you'll see that we are importing all the torch and matplotlib utilities. We're reading the words just like before. These are inconsequent words. There's a total of 30,000 of them. Here's a vocabulary of all the lowercase letters and special dot. Here we are reading the data set and processing it, and creating two splits, a train, and a classic split. Now in MLP, this is the identical same MLP, except you see that I removed a bunch of magic numbers that we have here, and instead we have the dimensionality of the embedding space of characters, and the number of gradients in the memory. And so I put them outside here, so that we don't have to go and change this back from time to time. With the same neural net with 11,000 parameters, that we optimize now 200,000 steps, and that's just at 32. And you see that I refactored the code here a little bit, but there are no functional changes. I just created a few extra variables, a few more comments, and I removed all the magic numbers. And otherwise,
I like that he has this forward pass implemented by him, you know. This language is fucking broken. Okay. Alright. See, like, why is... Oh my god, dude. It's just cache miss after cache... I don't know what it is, but... Clearly I'm misusing it, but you know.
when we optimized, we saw that loss looked something like this. We saw that the train and value loss were about 2.16 and so on. Here I refactored the code a little bit for the evaluation of arbitrary splits. So we pass in the string of what split we want to evaluate, and then here
oh, that's nice. We could implement that. The thing is, and the thing is, this is so crazy because it's like, it's not parallel pre-compilation either. It's like total fucking bullshit. So hopefully now we finally have a normal startup after 3 startups. And somehow I still feel like I'm gonna get a pre-compilation thing. It's incredible. It's just so stupid. So absurd. Okay, but we're in this one. So we want this. Okay. Alright, so we got our vocab. We got our dictionaries where we map to the index. We got these parameters. Here's where we build the model. So we're starting to use Flux now, just to make some stuff easier. Mainly, it was for some reason, and I don't know why, and it would be awesome to know why. But the training. Oh, this is Flux as well. In makemore 2. I have, manually written out all of the weights and biases. And then here is the forward pass. And it's a pretty simple forward pass, right? You just do the tan H, and then you do the, So it's a pretty simple. This is just a bunch of reshaping. Anyway, so it's identical, I think. And then here's where I do a train loop. And here's where I compute the gradient. So this is the forward pass that computes the loss. And then all I do is I take this gradient object that returns a grads object. And a dictionary-like container. Anyways, so then I try to do this where I just do gradient descent, but the minimum loss I got was like 4, which means it's like not something is. It means something's wrong. Anyway, so once I switch to Flux, let's keep going. Shuffle the words. Get dataset does a Oh, did I shuffle? Yeah, I shuffled the words, right? So I shuffle the words, then I get a dataset using the shuffled words. So this is all the X's and Y's. So this is okay, whatever. Then we get the train index, the dev index, and then we make our splits. So this makes our splits. And then we test that the full data set is equal to the concatenation of all of them. That's good. That means we're not missing anything. That was just a test for me. Then we build some iterable data loader type thing. Then we make a state of losses. And then here is where we train our neural network. Okay, and then we compute the loss on the train set, 2.57, and on the dev set, 2.57. And I think that this, let's see, what is our batch size right now? 32. Okay, run it again, 2.52. Anyways, the thing that I noticed is that in Flux, even though I think this is an identical model, I'm not really getting, anyways, we can do a, anyway, so you sort of get this thing. You can also do this to get maybe a better sense of scale. Then, okay. And, alright, so then we can look at what the generations look like. So these are some of these names. Tajil, Gomo Seduri, G, Egrau, Lari. I mean, these are all things I would name my children. So then we did another thing. The thing is, so we had an embedding dimension of 2. So this was supposed to be 10 later on. But the cool thing about this, so when you train with the dimension of 2... Wait, I thought I made a... Wait, hold on. I think I have to commit some code. Let me go get my laptop. Okay, yeah, I don't know. I feel like I made a function called embedding visualization plot or something. So we're gonna have to fix that. Oh yeah. All right. All right. So should be able to do. Okay. I don't know what. All right. So let's just run through this thing again. Oh, we made a generate function too. Oh no, we already had that. Alright, so let's just do this. We're gonna run through there. Okay. I mean, let's get on to the next stuff because this is like alright, there we go. What is that? That's the log 10 okay, but did I change the batch size? Yeah. And then I did want to test it on the GPU. I thought maybe that would be fun. Alright, so now let's just okay. And then do we have this? So the thing is, with 10 dimensions, you actually lose some of the like independence that you had. Like if you look at this, if you take any two dimensions, the first two, for example, I don't know. You need to go into the numbers to get a better understanding of how these things fit together. Okay, so let's just move on into this lecture.
And then this is the full passive network and valuation of the loss.
I gotta do something.
So just making it nicer. One thing that you notice here is I'm using a decorator, which you can also look up and read documentation. Basically what this decorator does in documentation is that
Test. Fuck. On my laptop, it gets rid of this. It thinks it's noise. Let's see. I got an idea. Wait, actually? Hold on. This kind of sucks, but we'll see if this works. Just so I have a setup that works on this. Whoa, that's noisy. Is it just super loud? That's insanely noisy. But only in one ear. Fuck it, fuck it, fuck it, fuck it. Okay.
So if you're not looking it does track with gradients in anticipation of the gradients. It's almost as if all the terms that they created have a required grab of the pulse. And so it just makes everything more efficient because your terms will I will not well any instrumentation, you don't need to return the graph. So that's what this does. You can also use the context manager with the graph. Then you have the second model. See that much nicer than words and stuff. It's still not amazing, but it's still not fully, but it's much better than the library problem. So that's our starting point. Now, the first thing I would like to speak about is the translation. tell that our number is very improperly configured at initialization. And there's multiple things wrong with it, but let's just start with the first one. Look here on the 0th iteration, the very first iteration. We are with this up. It's rapidly comes out. I can tell that being
Jesus.
in this case, I do not expect to sum. I expect to have any good company together. Basically, at initialization, what we want is that there's not state characters like the comments of any one state. At initialization, we have no reason to believe any characters to be much more likely than others. And so we expect that the problem distribution that comes out initially is a uniform distribution signing without only 20 state characters. So basically what we want is the probability for any character would be roughly 1 over place. That's all the circle. And then loss with a negative log probability. So let's wrap this into a circle. And then down we take the log bit. And then the negative log probability between loss and which is not much lower than the last. And so what's happening right now is that at initialization, we don't want this green probability distributions that are almost some characters are very well, some characters are very well. And then basically what's happening is that the network is very well. We have inputs that line up and we are very, very close to 0. And when we take the softmax of all zeros, we get probabilities that are a diffuse distribution. So it stops to 1 and is exactly uniform. And then in this case, if the label is saying 2, it doesn't actually matter if the label is 2 or 3 or 0, because it's a uniform distribution. We're reporting the exact same loss in this case. This is the one we would expect. Now, once that doesn't start repeating these logits, we're going to be changing the loss here. So it could be that we lock out, and by chance, this could be a very high number, 1 to 5. And this makes it very low, because we're assigning the correct probability at initialization by chance to the correct label. Much more likely it is that some other dimension will have a high negative. And then what will happen is we start reporting much higher loss. And what can happen is basically the logits come out on something like this, and they take on extreme values, and you can really high loss. For example, so these are uniform, so we are slowly distributing numbers form. And here we can also print logits, probabilities that come out, and so because the logits are near 0, the most part the loss that comes out is okay. But suppose this is like times 10 now. See, because these are more extreme values, it's very unlikely that you're going to be guessing the correct update. I mean, your confidence is wrong, and you're very less. If your logits are coming out even more extreme, you might get screwed. Yeah, so basically, this is not good. I don't want the logits to be not from 0. In fact, the logits don't have to be just 0, they just have to be equal. So, for example, all the logits are 1. And because of the normalization inside softmax, this will actually come out of. But by symmetry, we don't want it to be any arbitrary positive number. We just want it to be all zeros and we want the loss that makes that initial. So let's not quickly see where things go wrong in our example. We're the initialization, but the initializing wrong. And here, let me break after the very first iteration. So we only see the initial loss, which is 27. So that's way too high. And intuitively, now we can expect the variables to evolve. And we see that the logits here, which is print these, we just break the first row. We see that the logits take on quite extreme values. And that's what's creating the big confidence in incorrect answers and makes the loss get very, very high. So these logits should be much closer to 0. So now let's think through how we can achieve logits coming out on the 0 lot to be more closer to 0. You see here that the logits are calculated as the thin states multiplied by W2 plus V2. So first of all, currently we're initializing V2 as random values of the right size. But because we want roughly 0, we don't actually want to be adding bias of random numbers. So in fact, I'm going to add a times 0 here to make sure that V2 is just basically 0 at the initialization. And second, this is h multiplied by W2. So if we want logits to be very, very small, then we would be multiplying W2 and making that small. So, for example, if we scale down W2 by 0.1 oblions, and if I do again just the very first iteration, we see that we are getting much closer to what we expect. So, roughly what we want is about 3.29. This is 0.2.
Wait, why do you want 3.29?
Then we would translate. Do again just the very first iteration, we see that we are getting much closer to what we expect. So, roughly what we.
Oh, right. The log of uniform.
Now, you're probably wondering, then we get, of course, exactly what we're looking for at initialization. And the reason I don't really do this is because I'm very nervous, and I'll show you in a second why you don't want to be setting values or weights of the neural net exactly to 0. You usually want to be small numbers instead of exactly 0. For this output layer in this specific case, I think it would be fine, but I'll show you in a second what this is wrong, right? So let's just go 0.01. In that case, our loss is close enough, but has some entropy. It's not exactly 0. It's got some entropy, and that's used for symmetry, as we'll see this. Logits are not coming out much closer to 0, and everything is wrong. So if I just erase this, and I'm now taking away the brace, we can run the optimization with this new initialization, and let's just see what losses. Okay, so I went on, you see that we started off here, and then we came down a bit. The block of the loss. Now it doesn't have this hockey shape appearance. Because basically what's happening in the hockey stick, the very first few iterations of the loss, what's happening during the optimization is the optimization is just squashing down the weights, and then it's rearranging the weights. So basically we took away this easy part of the loss function, where just the weights are just being shrunk down. And so therefore we don't get these easy moves in and we're just getting some of the hard things training the actual neural. And so there's no hockey stick appearance. So good things are happening from both. Number one, loss initialization is effect. And
But if it's only for a few iterations, why does it actually even matter?
The loss that came out is actually quite a bit. Unfortunately, I erased what we have here before. I believe this was 2.12, and this was 2.16. So we get a slightly improved result. And the reason for that is because we're spending more cycles, more time, optimizing the neural net actually, instead of just spending the first 7,000 read how we use it.
Should we test it? Wait, what happened? What does it give it? Do I have to do this maybe? Damn, how do you do that? Can I just I can just manually do it, I think. I can just go like this. And do model dot layers 4 dot it doesn't complete. Dot Oh, hey, that's interesting. It initializes my biases to 0. Note that dense layers init bias to 0. So that's already something different. So we're just gonna take this, just say equal to and then presumably that. Okay, so we can just do that. That's how you do this. And I think he said 0.01. And he did it for what? Where's the chain? Okay.
Focus on not block the loss. Now it doesn't have this hockey shape appearance. Because basically what's happening in the hockey stick, the very first few iterations of the loss, what's happening is the optimization is just squashing down the weights, and then so basically we took away this easy part of the loss function. Yeah, so therefore we don't get this easy ways of and we're just getting some of the hard things to turn the so because the loss that came out is the time optimizing the second part. Let me reinitialize our brain, let me reintroduce the so we have reasonable actions. So even though everything that we have about loss gets us back, we're still we're probably built with this as the one that's in fact.
Okay, so we did that, and we reinitialized it, and this is the training, but we want to evaluate the loss. Oh yeah, here. So we can just do loss. Yeah. 3.29. Nice. So if we want to get H, how do we actually get an intermediate? That's kind of annoying, right? Or no, wait, can we? Because H is... It's in makemore 2, right? H is this. Let's go to the we can go to the last one. Yeah, so H is that hidden part after the tan H. So okay, so let's just rewrite that. So H is equal to how do you run a chain? You want to run it up until there. What? What is that? Yeah, it's compose. What the fuck is this? Oh, you can. Fuck. There we go. What? Reverse of tuple? What? Oh, you know what it is? No, this is gonna work. It's that we have to do this. Alright, can we call this on an input? Wait, X is not defined? Oh. Oh, nice. Sick. There we go. Bam, baby. I knew I could figure that shit out. This is where we're at. So, but can we just do it on a couple of examples? Like 1 to 5. 200 by 5. Let's get wait 200 by 5. Oh, that's the okay, yeah. Let's get a nice square matrix. And then we could do a abs dot h. What is does this do anything? Yeah, that's what I figured. But that's actually what I want. So abs this dot greater than 0.99. Keep none of that. So there's all of these maxed out guys. Okay. I'm pretty sure that's where he's going. Ooh, let's try to do that. Okay, wait. So let's try to train the neural network. I wonder if this works. Nice. So now let's just check model.layers end dot weight. All right, cool. So that worked. That's hype. I like how easy that is. And let's just train it for one epoch. And then let's do a um um yeah, it doesn't do very well, but why doesn't it do very well? Wait, can we check the loss? So after we initialize this thing, we actually want to oh yeah, um we want to get the loss. So we want to do this on the train set. So we initialize it to 0. We do this. And the initial loss is kind of what you expect. Wait, can we give this an init or no? Let's see. Oh yeah, we have it. Identity init. I don't know what that means. All right, so let's do init. So that worked, I guess. I don't know. Did it say only of the other ones? Okay, so the initial it's the same. But should we do the forward pass ourselves? We have the loss ourselves. I think it's here, right? There we go. It's like why rewrite it? I've written it enough time. We should be able to. So model of X. This include. Oh yeah, wait. We should let's just do this. YOH 1 hot. Oh yeah. Let's just do this. Who the fuck cares? Okay, we got the loss. Okay, so the loss really is that. Wait, what? Oh wait, that no, okay. Um, didn't I fix this thing? Whatever. I'm pretty sure I found a better way to do that. Oh no, I think it was just a column age. I think. Wait, is this X? No, this should be a. Oh, I fucked it. Wait, what am I doing, bro? Answer. Um, because this is a whoa. I guess that makes sense. They're all equal. Uh, can I just do this? Does this work? Lol. Okay, I don't really care. Alright, so, but let's try to train it. Plot the losses. Okay, I mean, it goes down for sure. But it bottoms out. I guess does it bottom out? Let's try, we have learning rate decay, so let's just do 3 epochs, just to see what happens. And let's look at some of the generation, too. So, okay, so it flattens out, but why? I'm guessing, yeah, these names are terrible. Okay, inspect the gradients and activations to figure out what is happening and why the network is only partially learning, and what part is being trained exactly. So wait, let's look at the embedding. Oh my god. Wait, is that true? Wait, what if we don't init the Alright, so let's run this back. Uh I guess it's changing, but it's barely changing. Okay, well, I don't know. The hidden state, basically nothing is being activated when you initialize the weights to 0. But why? Okay, well, in any case, let's keep going. Let's see, can we just do a histogram of a matrix? Wait, what the? Oh, wait, no, but this is because this is, so let's, go back to,
the builders and the arts application to access of everything that's built in the along with that, there's distribution of energy, which is a more strong. So eventually, we have to remember during that knowledge, just like we saw right now, we are doing backup tasks, starting with us, and then through the network files. Particularly, we're going to back up through this contact image. And this layer here is made up of 200 neurons, 800 examples, and implements the deployment of image. So let's look at what happens in 10 to 2 hours. We'll actually go back to our previous microgram code, the structure, and see how we implement it. We saw that the input here is x, and then we calculate t, which is the 10 x. So that's t, and t is between negative and 1, it's the output of the 10. And then in the micro class, how do we back up into 10? We take out that graph, and then we multiply it, it's the chain with the local restricted form of 1 minus t squared. So what happens if the outputs for 10 are very close to negative 1 or 1? If you plug in t equals 1 here, you're going to get 0, multiplying that graph. No matter what that graph is, we are killing the gradient. And we're
Oh, damn, that's sus, bro. That's sus as hell. Yeah, you don't want that. You definitely don't want to kill the gradient.
And so changing basically the input is not going to impact the output of the 10 too much because it's in a flat region of the 10. And so therefore there's no impact on loss. And so indeed the weights and the biases along with the standard unit do not impact the loss because the output of the standard unit is in a flat region of 10. And there's no impact you can change it in whatever you want. However you want, the loss is not down. That's not a way to justify that. Indeed, the gradient would be basically 0 if that is. Indeed, when t equals 0, we get 1 times that graph. So when 10h is some exactly value of 0, then that graph is just passed through. So basically what this is doing is if t is equal to 0, then this the 10h unit is inactive, and the gradient just passes through. But the more you are in the flat tails, the more the gradient is split. So in fact, you'll see that the gradient going through 10h, the only number of decrease in the amount of decreases is proportional to the square root, depending on how far you are in the flat tails. And so that's kind of what's happening here. And through this circle, that all of these outputs are in flat regions of greater than 1, then the gradients that going through the network will strong like this. Now, there is some repeating right here, and that we can actually assess with our transcripts. Basically, what we want to do is we want to take the absolute value and see how often it is in a flat say gradient. Which is value. And this is Boolean tensor. So the Boolean tensor, you get a white if this is true and a black if it's false. And so basically, we have 32 examples and 280 neurons. And you see that one of this is white. And that's telling us is that all these 10H neurons were very, very active and very flat tail. And so, in all these cases, back gradient would get straight. Now, we would be in a lot of trouble if, for any one of these 200 neurons, if it was the case that the entire column was swept. Because in that case, we would called a dead neuron. And so it could be a 10H neuron with
I wonder if we can make a little animation of for every one of these. It's gonna slow it down a lot. We'd have to manually do the forward pass, which is fine. But it would be cool to visualize it training for sure. Wait, did my... Oh, wait. There we go.
And so just scrutinizing this out for any slope, we see that this is the case. So I don't see a single neuron that's all right. And so therefore it is the case that for any one of these 10H neurons, we do have some examples that it's a cycle that's local to the low neuron rotating. But because of the event or something, this is where that dynamics and biggest manifest is that no matter what input you put in, this 10H neuron always fires really one. That's what we say about this is not specific for a third time. So certainly use that. Let's say we'll have a massive because it is expression. It's a single truth is but it's a single the single also not to run. So really so when you run So to get, for example, get running one, or to get running one, basically like that. Basically what it is if I'm near with a running one world, never activates. So for any example of running with this, it never turns down. It's always in its ground. And there's no world is equal to its weights and bars. We never get it. We never get it. And this is sometimes happen in initialization because the weights and bars just put so much on chance somewhere else that doesn't belong there. But if you have like if you have like a 200 loading rate, for example, sometimes you have to realize that there's too much for bigger and you get knocked out of the data. This is that. From then on, no example comes. This is where zero remains like forever. Just stay on it, remain permanent. And so sometimes what happens, if you're running with a Python problem, you have no running once. You train the wheel around with some stats.
Dude, he really does know the dark arts. Kind of crazy.
So usually he's running around changing readings, and when you put up a reading, somewhere by chance, you get bumped off. And then nothing happens from then on, so that's kind of but these other nonlinearities, well, we rarely will not suffer from this issue as much. If you can see that doesn't front towards the percentage difference. And he was also quoted for the reason that also has this issue with this black box. So that's just something to be aware of as I say that. But in this case, we have way too many which is that's a bunch of things. And because there's no knowledge of that, I think we would be okay and we would have this but it's just not like that. It's something like that, especially in English language. And so basically.
Oh, hey, wait. Why don't we jump the gun here and change the initialization to okay, so with glow rot uniform. Wait, first we're gonna let's do the plot. Up here. Okay, so we do this. Wait, let's just I mean, everything's still dead. Oh, no. There's only a couple that are dead. So wait, so let's go back to but these aren't technically dead. But it is the case for the white ones that we start off with a very high amount of them that are on the tails. And the thing about the tails is yeah, yeah, okay, so let's redo it. Okay, we're gonna initialize. We see that there's in this case, none that are greater than. There's a few greater than 0.9, but that, I mean, if we just do the histogram, the initial histogram of the weights of the after the nonlinearity, they are way more uniform, way more normal. So that's cool. So we look at the loss. The loss starts out, I guess it's the same. That's sort of what we saw in the other case. We're getting a pretty good loss. Let's plot the losses. That's pretty good. Train loss, yeah, 2.18. Homie, Lynn's a real name. Yano Hani. Krista Tofton, I don't know about these. Let's train it for a little bit longer. Yeah. Nah, Eugen. Anyways, why don't we just make H the composition? Why do we have to make H the fucking... Let's call it HF. HF is the composition of the first three layers. With the function. So then wait, let's undo this. So we want this. Redo. Okay. Alright, so we should be able to just do HF, the hidden function. Okay, the thing is, some of them did sort of get pushed outward. So, interesting. So, it's not nearly as bad though. We have like, it's not nearly as bad. Damn, see, he's getting such good fucking numbers, man. What the hell? Wait, can we look at our validation loss? I think our validation loss is it dev? I think I call it dev. We're getting 2.19. And for this to be on a log scale, it means that 2.1 is way better than 2.2. And I'm using glow rot. Hmm. Oh shit, hold on.
Just like here, in this case, the multiplication. And what does mean is standard deviation of reductions. So in the beginning here is just a random function means that and standard deviation is one. The standard deviation of is just another spread. But then once we multiply here, we see that the mean of course is the same. So that's the but we see that the standard deviation is the standard deviation. It's the standard deviation is about the one. So we see that the standard deviation is standard. And so what's standard is and we don't
Is there like a principled math way to do that? Like the product of Gaussians is Gaussian, but with scaled standard deviation. I feel like there's something there. Oh. Yeah. Okay, so wait, let's see if we can find flux.chi. So I should just be able to put this. I mean that, that looks right. So let's just put this in here. And let's try to see if this works. Cool. Get our heat map. The thing is, wow, chiming normal. Let's look at the histogram. The histogram before the heat map makes sense. I mean, a lot of it is saturated. I mean, compare that to in any case. Um, hey, whoa, these are great. Let's keep going. Oh shit! No, 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 wait. I mean, yeah, better, significantly better. A lot is saturated, but the names are good. Wow. I mean, yeah, the initialization matters way more than I realized.
So if you're allowing your feet adjust, so it's really good. Allowing your feet to rest, or your feet to and so we see that, for example, it's getting destroyed. The reason it's destroyed because there's a see how the two is inside, so it's a getting destroyed. In the case of me, we just get the because challenge is so last year was a literally the only contract challenge. It's challenge, just like running, is a contracted testimony. So that means it's particularly up the distribution of the to be more special in the summer. Now, running stretches about taking everything over the open back to throw. Kenny goes this way, so because it's taking tails, squeezing in. So when you park it, squeezing in means to boost the weights lower so that we don't make it back to the previous. So that's why I'm going to now, instead of these a little bit bigger, I'm going to actually and these flags, because about 7 years ago, this video was you have to actually be two of the applications of readers, but just Instagrams, and you have to be very good at accessible things and supervisor. And I think it's very key for adult people, very big, especially for them. But there are a lot of ways to make it, so we have to most of it more, and unless it goes to the ones that was exactly right. And some of this one really just because I don't part, there's a treatment test, which is very you saw a number of so all these non-related that's able to obsessive all that means something like this what can be that's to Irish ones they basically just one is my basic story it's basically what they do so I always be something we go back makes it up and this is how you have to set the standard with me over Australia and so set the standard of mix from the business house it's going to be let's say two problems the examination is it's about very obviously the techniques and the methods too that basically scales down and that basically it's basically the number that we're not there that it's so here this is about examination of two simple but we have to set examination to make the work starting with the problem so in other words yeah there's no challenge is square root and this is a good understanding. I just noticed actually the W1 is actually one by 20 instance. It's actually only both actually purple. And that's because we can't perform much of the feeling. It's actually a family here is 30 but this being a 30 so this is the number. This is what our segregation belongs to. It's not much something whereas here just by feeling the distribution
So wait, actually though, so can we look at the function there then? So this takes the dims. Okay, so yeah, right. It also takes an RNG. Okay, that makes sense. Fan in. There you go. Square root first and fan. Weird. Yeah, I mean, he's basically just like, as you scale this up, there are growing pains. These are the growing pains that people found.
and we're talking about how we don't want these reactivation states to be way too small for the mechanic is not but we don't want them to be too large, then the 10 inches is too high. In fact, we want them to be roughly large, so 0 meaning and units around 10 inches, at least 6 inches. So the insight from Dr. Thomas' paper is, okay, you have these instincts, and you'd like them to be roughly matching, then why not take one of these things and just formula them to be matched? It sounds kind of crazy, but you can just do that because standardizing instincts so that the function is a perfectly functional operation. So that was kind of like a big insight in this paper, and when I first read it, my mind would blow, because you can just formalize instincts from just what mistakes in the level of these conditionalizations. You can just formalize them to even function. So let's see what happens. So that just was one of the actions here just before we enter into the test. The idea again is we're moving to make this roughly large. And that's because these are way too small numbers that we make the ratio is. But if these are very large numbers, then the 10 inches will just saturate it. We want this to be roughly large. So the instant came.
So it's actually part of the.
So yeah. So here,
So what we're gonna do, is we're gonna implement batch norm, but we're not gonna use, because I'm pretty sure they have a batch norm thing obviously implemented. So I feel like we want to implement it all by ourselves. Let's make HPF too. So this is just the embedding. Like, this is literally just the embedding. Wait. Is that right? Or is that literally just before the... No. See, okay. So what we want is... so we want x2 of x times model dot layers 3 dot, and we add the bias too, dot weight. Is it weights or is it weight? I thought it was just weight. Yeah, I don't know what the fuck it's talking. Plus, and I think, okay, wait. First off, let's... And then how do we do this? So we have HP, then B is equal to model.layers3.bias. Oh, but it's 200? What? I think we fucked this up. So what is the shape of this? This is 200 by 30. And X is going to be... It would be interesting if we could just split these out. So so then let's just make this. So this is L1. I'll just call it L1. I don't really care. L2. This is the final. So now we should be able to delete this and make this just emb reshape permute. So now we at least have names where we don't have to keep doing the fucking... Let's just see if this works. Oh yeah. What happened? Oh, did I not? Oh wait, hold on. Oh, the commas. Okay, cool. So we have the model. Now what I wanted to do is look at HP React. So what we're gonna do is we're gonna do we could do this composition thing, but I think what I can do is just so we have, so what is X? X is gonna be X is 1 to 200 like this. So the first 200 examples. And then we're going to put this into m. So m of x should just work. Right. Right. Then we have to call reshape permute on them. And we get 30 by 200. And now L1.weight is 200 by 30. So I'm pretty sure... Wait, does this tell me the shape tracking? Because I'm pretty sure if I do this, and then I do L2, or wait, then we calculate HP, and then we do L2 of HP, this is going to fail because of a dimension mismatch. So I'm pretty sure I actually need to put this over here. It's going to be, and then this is the composition of these functions, and this is going to be this. Okay, let's try that. So now if I do this, I get a 200 by 200. Oh, that checks out. That's right. It is 200 by 200. So then HP, but we forgot the bias. So wait, we got HP, and then we have L1.bias, and this is 200. HP, oh, fuck, wait, can we make this not 200? Make this 100. So HP should be, wait, what? Oh, because we needed X. Okay, so this is HP. It's 200 examples by 100. Or no, it's 200 embedding dimension by 100 examples. So each column, right, which actually makes sense based on the memory layout of Julia. And so, but what we want to do is we want to do a, and I'm pretty sure that I can just do a dot plus. And then if that works out, so this is actually HP React. So we just want to put this here. Let's see. Okay, cool. So this is the pre-React. And why did we care about that? Oh, because we need the mean of it. Okay. So now we should be able to take this, which we don't want, here. Or we could keep the pre-React function here. We can delete this though. And then X is like a mini batch, I guess. So here's our pre-React. I'm going to call mean of HP. Okay. Oh, wait. Along the first dimension. 1 by 200. Oh, because that's a batch. So wait, mean, and then, let's see, mean. Presumably there's a matrix mean where I can, there you go, mean dims 2. And that might be right. 200 by 1. Yeah. Because the reason why it's 2 and not 1 is just because it's permuted. So there we go.
So here we are calculating the mean, which is just taking every value of any nuance function. And the standard deviation is basically kind of like this measure of spread that you can use it, which is the distance of every one of these values away from you and back. That's the variance. And if you want to standard deviation, the square root of the variance to get the standard deviation. So these are the two that are calculated. And now we're going to normalize or standardize these x's as capital mean and
Wait, what is y in this case?
so
Oh, y is the output. Okay. Gamma and beta are the parameters. The values x over mini batch b, x1 to m. Batch norm of the parameters, and what is xi? Oh, yi equals xi. Okay. Alright, you take the mean, that's a scalar. Then you take the variance, that's also a scalar. Then you... Wait, why do you do the... I'm kind of curious why you do this scale and shift part.
So basically, standard deviation. It's exactly what these two, FTD and mean, are calculating. This is the mean, and this is the variance. You see how the sigma is the standard deviation usually, so this is sigma squared, which is variance to the square of the standard deviation. So this is how you standardize these values. And what this will do is that every single neuron on this primary node will be exactly the fraction of these according to geometric the function happen. We are normalizing these factors. And then we could in principle train this. What is that? Calculating the mean and the standard deviation. These are just mathematical formulas. They're perfectly differentiable. All this is perfectly differentiable, and we can just train this. The problem is we actually won't achieve a very good result with this. And the reason for that is we want these to be roughly Gaussian, but only at initialization. But we don't want these to be forced to be Gaussian always. We want to allow the neurons to move this around, to potentially make it more diffuse, to make it more sharp, to make some 10-inch neurons maybe be more trigger happy, or less trigger happy. So we'd like this distribution to move around, and we'd like the backpropagation to tell us how the distribution should move around. And so in addition to this idea of standardizing the activations at any point in the network, we have to also introduce this additional component of behavior here described as scale and shift. It's basically what we're doing is we're taking these normalized inputs and we are additionally scaling them by some behavior and positively by some else to get our final output from this network. And so what that amounts to is the
Oh, dude, this whole thing is a pseudoscience, bro.
and then so they have a B of bias, which will be close to zeros. And then also be a shape and that. And then here, the B in gain will multiply this, and the B in bias will offset.
That's silly as hell, dude. Alright, so should we do it? So we want... Alright, so we want this. So, okay, so... Why is that giving me a method error? I think it's probably because I have to do a type of thing, but I don't know. S is going to be, okay, cool. And so now it's going to be HP minus U. Wait. Alright, so that worked. The BN gain was what? Ones, 1 by... What did I call N hidden? Okay. And the bias is just zeros. Oh yeah, right. That makes sense. And yeah, because they start out with one gain. That okay, that checks out. I don't know why I'm just copying. That checks out. So then you do a dot times like this. No, oh, wait, hold on. Oh no, because this has got to be. Hold on. This is 1 by 200. Let's see. This is the So this is the norm HP. Okay, then so this is 200 by 100. So we want so this actually needs to be n. Oh no, what? That should be fine. I think we just need to do this. That seems wrong. Bn gain is 1 by 200. Let's see what he says the shapes are going to be.
B in gain will multiply this, and B in bias will offset. So because this is more possible, this is 0. Neurons are in values from this value.
Yeah, see, I feel like I'm transcripts anymore because this is 200 by 100. I think I do want to do this. Wait, can we get rid of this fucking thing? Okay, so okay, yeah, there you go. So this needs to be n hidden by 1. And so does this. So we have this, this, dot plus bn bots. There we go. So now if we are to take the, so this is going to be the bn HP react. So this is what we take the tan h of, I guess. But so now what we should see if we, so wait, let's look at U. Let's look at normed HP. So this, what it's saying, so it's 200, which is the, so if we take the first column of this, oh wait, wrong way. And we were to just, histogram it, we would see, wait, that's 10 bins. How is that 10 bins? How is that 10 bins? You freak. Okay. But what am I trying to actually do? What I want to know is, because this is, you're basically you're coupling the examples in the batch. So you got this batch of 100 examples. Dude, this whole thing sets off my freaking sus meter. This whole thing seems sus.
And then during optimization, we'll be able to back calculate to be able from the bias mutation, so the network is given the full ability to do with this whatever it wants internally. Here, we just have to make sure that we include these in the parameters of the neural net because they will be trained in that calculation. So that's the chance. And then we should be able to type. And then we're going to also copy this line, which is the nationalization layer. We're going to set a line point. And we're going to swing down there, and we're also going to do the exact same kind of testing. So similar to training time, we're going to normalize in that scale, and that's giving us our training validation rates. And you'll see in a second that we're actually going to change this a little bit, but for now I'm going to do this one. So I'm just going to wait for this to print. Okay, so I allowed the neural nets to converge here. When we scroll down, we see that our validation loss here is 2.10 roughly, which I will get here. And we see that this is actually kind of comparable to some of the results that we achieved previously. Now, I'm not actually expecting an improvement in this case. And that's because we are dealing with a very simple neural network that's just a single layer. So, in fact, in this very simple case, like this one layer, we were able to actually calculate what the scale of W should be to make these pre-activations already have a roughly larger shape. So the batch normalization is not doing it here. But you might imagine that once you have a much deeper neural that has lots of different types of operations, and there's also, for example, residual connections, which we're covering, and so on, it will become basically very, very difficult to tune the scales of your weight matrices such that all the activations throughout the neural net are roughly partial. And so that's going to become pretty intractable. But compared to that, it's going to be much, much easier to sprinkle batch normalization layers throughout the neural net. So in particular, it's common to look at every single linear layer like this one. This is a linear layer with analyzed matrix and having bias. Or, for example, combinations, which we'll cover later, and also perform basically a multiplication and matrix in a more station structure format. It's customary to take this linear layer or evolutionary layer and depend the back layer on the scale of these activations at every point in the neural net. So we'd be adding the back
So wait. So what we're saying is that the embeddings here if you were to look at for each, let's see, hold on, let's think about it. So you have 200 of these means, and there's 100 examples. Right, you're taking the mean across the example dimension. Okay. All right.
Now, the statement of dimensional notation actually that process that people don't have something terribly strange and unnatural. It used to be that we have a single example being before, and then people create calculations and phases, and this is a deterministic sort of process. So you arrive at one instance. And then, because of efficiency of training, we suddenly started to use batches of examples. But those batches of examples were processed independently, and it was just inefficiency. But now, suddenly, in batch normalization, because of the normalization of batch, we are coupling these examples mathematically and in the forward batching algorithms. So now, the dependency graph is state graph, and your emergence of any one given example are not just a function of that example of its input, but they're also a function of all the other examples that happen to
Yeah.
in that batch. And these examples are separate. And so what's happening is, for example, when we look at HPI, instead of even 2H, it means the calculations for example, for any one of these different numbers. It's going to actually change slightly, depending on what other examples they've already batched. And depending on what other examples happen to come around, H is going to change subtly, and it's going to jitter if you imagine several different examples. Because the statistics of median distribution will be different. So you'll get a jitter for H, you'll get a jitter for emergence. And you think that this would be a bug, or something that is relevant, but in a very straight way, this actually turns out to be good in real life. And it's the same. And the reason for that is that you can think of this as kind of like a regular bicycle. Because what's happening is you have input into H, and then depending on other examples, it's jitter. And so what that does is that it's effectively padding out any one of these different examples, and it's introducing a little bit of entropy. And because of the padding out, it's actually kind of like a form of data augmentation, which is so by introducing other tools, it's actually has other examples, regularized. And the part of using seemingly a secondary effect, this is actually a regularizer, and that has made it harder for us to remove the use of rationalization. Basically, no one likes to stop to that the examples in natural top of mathematics and inquiries. And it leads to all kinds of strange results. We're going to see that in a second moment. And it leads to a lot of thoughts. And so no one likes to stop to. And so people have tried to.
What else is in the playlist?
Exactly. Your normalization, business normalization, group normalization. So we'll understand these. But basically, long story short, batch normalization was the first kind of normalization that we introduced. It worked extremely well. It happens to have this normalization effect.
So maybe we'll skip some of this PyTorchification because I do really want to. I'm like, bro, this fucking thumbnail is awesome. Yeah. What's in this one?
So today we are once again continuing.
Oh. Oh, that's actually so pathological for a sigmoid. Yeah, but the thing is, it's like, is sigmoid just bad then? Maybe that's why sigmoid is so bad. All right, let's keep watching. Let's keep watching. Raylu also seems like it sucks. Can we just try Raylu? I mean, this is, for fun, right? How good does Raylu do? Well, Raylu's hella fast though. That's kind of crazy, bro. Can we fucking? Okay. Okay. So, yeah, maybe we should do this one. This one seems like we should. Sit down with a pen and paper and just do each layer. Maybe not do the batch norm. I feel like I don't know. I don't know how much of this I need to do. Yeah, because look, he's backpropping the batch norm and the cross entropy loss. Right, yeah, it's like mostly about the batch norm. I kind of really want to watch this one though.
So by now, we just create all the characters. So we're going to take all of the stuff in Shakespeare into this. So in particular, we're going to take the first 9% of the data set and consider how many of them are going to replace the last 1% and implement it in the knowledge data. And this will help us understand to what extent our models are fitting. So we're going to basically hide and keep knowledge data aside because we don't want to predict their value. It's down to HTTP. We want a neural network that sort of HTTP text. And so it should be fairly likely for it to produce the actual stowed away sort of specificity transformer so that it can train and learn those things. Now, the important thing is whenever we actually feed entire text into a transformer all at once, that would be computationally very expensive. So when we actually train the transformer on a random data set, we only work with chunks of the data set. And when we train the transformer, we basically set random little chunks out of the training set and train them just chunks at a time. And these chunks are basically some kind of a length, this maximum length. Now, the maximum length typically, if using the IG and slope block size, you can find out different means, context length, or something like that. Let's do this just we are for 3 data characters. That's one and tell me what's wrong. This is the first 9 characters in the sequence in training set. Now, we're not going to have a second short data levels. So instead of these 9 characters in training set, this actually has multiple examples packed into it. And that's because all these characters are all total. And so what this thing is going to say when we publish total is that we're actually simultaneously trained to make prediction of every one of these conditions. Now, in the chunk of 9 characters, there's actually 8 individual examples packed in it. So for the example that when 18, in the context of 18, 47 public teams. In the context of 18 and 47, 56 public teams. In the context of 18, 47, 56, 57.
Yeah, but like that doesn't actually make sense. I feel like that's silly. Like if you're not actually at the start, because like
X are dependent features. You will just be the first block size characters. Y will be the next block size characters, so it's offset by 1. And because Y are the targets for each position in the table. And then here I'm iterating over all the block sizes. And the target is always all purchasing X up to 2, including 2. And the target is always the key character up in the targets for Y. So I'm just trying this here. And basically it spells out what I said in notes. These are the 8 examples in the chunk of 9 characters that we sample from the trains. I want to mention one more thing. We train on all the 8 examples here with context between 1 all the way up to context of block size. And we train on that not just for computation reasons because we have one sequence already or something like that. It's not done just for efficiency. It's also done to make the transformer network be used to seeing complexes all the way from as low as 1 all the way to block size. And we want the transformer to be used to seeing everything in 2. And that's what we use for later with this. Because while we're sampling, we can start second generation with as low as 1 character of complex. And the transformer knows how to predict this character with all the way up to just 1.1. And so then it can predict everything up to block size. And after block size, we're going to start chunking because the transformer will never.
I guess that makes sense. I guess he's right. But it is still like a bit of an abuse because it's like that part of Shakespeare wasn't the beginning. There was stuff before that.
So let me basically just generalize this tree slash and kick. Here's a curve. So here, we're going to start cycling random notations of the transform. I am setting C so that in the random notation here, so that numbers I see here are going to be numbers we see if we try to run this. But the backside here is how many events this is. We're processing every forward backward pass in transform. The block size as I explained is the maximum number slave to make those branches. So let's say process 4, process 8, and then here's what we get back. What we actually split. In the split is a training split, and then with training data, otherwise I'm not data. That gives us the data, right? And then when I generate random positions to grab a chunk out of, I actually generate batch size number of random offsets. So because it's 4, we have IX is going to be the first, a random generator equals 0, and then a data multiplies. So it's just random offsets in the training. And then so we have the offset by 1 of that. So it's that plus 1. And then we're going to get those chunks from every one of pictures I in IX. And we take total stack. We take all those one-dimensional transfer sets here, and we're going to stack them up at rows. And so they only have a row, and they 4 by 8. So here's my problem. Let's say we'll have X to be 1. We take this transform now. We get those X is the 4 by 8 circle, 4 rows, 8 columns. And each one of these is a chunk of the trains. And then the targets here are when you associate with a and they will come in with transform all the way to create the last picture. So they will give us the parameters for everything the picture is on X. And then these are the 4 independent rows. So spell out as we get 4. This 4 contains a total of 32 examples. And the completely independent as far as transformers concerned. So when the given string code targets infinity, or for infinity, whatever way, when you have string code for 3, targets 50. When you have string code for 58, targets a second. Well, when it is up 52 to 1, the target is 50. Right, so you can sort of see this spelled out. These are 32 independent examples packed in a single batch with X, and then the design targets are 1. And so now this integer cluster of X is going to feed into the transformer, and the transformer is going to simultaneously process these examples, and then we'll talk about integers to pick in every one of these positions in the transformer. Okay, so now that we have our batch of numbers that we have to feed into the transformer, let's start basically feeding this into row numbers. Now we're going to start out with the simplest possible row number, which in this slide is 9 in the diagram. And we covered the diagram level in our 8 series in the node now. And so here I'm going to sort of go faster, and let's just make the micro model directly, rather than this diagram function. So I'm going to go to the backwards module for this way. And then here I'm starting the diagram model, which is across the level. And then I'm calling it and passing the inputs in terms. Now the inputs are already here. You see that I'm sticking the index, the inputs X here, which I made into RDX. I'm just passing them into this 239 table. So the here is that we are constructing. We are creating a 239 table. And input size 4 by 7. And we're using an ML table, which is a very plain wrapper for our basically a circle K will have some negative size. And what's happening here is that when we pass IDX here, every single integer in our input is going to refer to this negative table, and it's going to pluck out a row of that negative table corresponding to the inputs. So 24 here will go to the negative table, and we'll pluck out the 24th row. And then 43 will go here, we'll pluck out the 43rd row, etc. And then backwards, we're going to rainbow this into a batch by time by channel tensor. In this case, batch is 4 times the C, which is done. Channels is 4 times 65. And so we're just going to work out all the rows, arrange them in the IT by C. And now we're going to interpret this as the widgets, which are basically the scores for the next step in the sequence. And so what's happening here is we saw a lot of this in the series, and here if I start this, then we quickly get predictions, scores, and inputs for every one of the 4 series. Now that we make predictions about the process, we have to evaluate the loss function. And so in makemore series, we saw that a good way to measure the loss or the quality of predictions is to use the negative log loss, which is also a good way to measure target name plus. So what we want to do here is loss is the possibility of the predictions and targets. And so this measures the quality of the loads with respect to the targets. In other words, we have the identity of the next character. So how well are we predicting the next character is the loads. And intuitively, the correct dimension of loads, depending on what the target is, should be very high number, and all the other dimensions should be very low. Now, the issue is that this won't actually, this will be what we want to basically talk about just and the loss. This is only one, but unfortunately, it's not actually data terms. But if you really want to terms, now we look at the approach, process tree, application group. We'll try to call the process tree in one single thing, so that is the one not different. But here we look at the documentation, you have to put details of how Python expects these inputs. And basically the issue here is Python expects if you make that measure into contribute because we repeat by t by c tensor, then it actually enables the channels to be with this measure here. So if it, so basically it knows that b by c dot instead of b by t by c. And so it's just the details of how Python treats these kind of things. And so we don't actually want to deal with that. So we're going to expand this in case we shape images. So here's what I want to do. I want to take this names to the meshes. So we'll just shape this b by c and then let's say that it's and we want to be times c, so just a measure, right?
There's no permute dims? There's got to be a permute dims view thing. Oh, weird. This is like the lame part of AI stuff.
So let's do the generation. Now I'm going to go again really fast because I covered all this in previous videos. So here's the generation. So we keep digging at the same time with the Python method. And basically, this is the current context of some characters in a batch. It's a batch. So it's also b by t. And the job we generate is to basically take this b by t and instead we b by t plus 1 plus 2 plus 3. And so it's basically improves the generation in any batch dimension in the time dimension. So that's the job. And we'll do that for max inputs.
Oh, it generates a batch? That's nice, man. I like that. Because my loop is inefficient. I loop, which is stupid.
So we get those time limits. And then the loss here, then we know because we're not using that, we have no targets, sort of round truth targets that are running here. Then once we get the logics, we are only focusing on the last step. So instead of b by t by c, we're going to fuck out the negative one, the last element in the time machine, because those are predictions for the constant. So that's the logics, which we then work probabilities, we ask softmax, and then we start out linear to cycle for these probabilities, and we ask factor plus 1 cycle. And so IDX will become b by 1, because in each one of the batch dimensions, we're going to have single dimensions for text. So the sum cycles equals 1 will make this beginning. And then we're going to take those integers that come from the second process from the probability distribution here. And those integers factors will concatenate above the sort of one stream of integers. And this gives us a multi-best one. And then we break it out. Now, one thing here is, you see how I'm calling solve of IDX, which will end up going through the forward function. I'm not writing any targets. So currently this would give inherent targets is sort of not moving. So targets is not. So targets is not quite fit. And then targets is wrong, then there's no loss to it, so just loss from else all this happens something loss. So this will make it so if we have targets we provide anything loss, the targets will just get the values. So this here will get rid of it.
It's kind of clean.
So these are the IDX, right? I'm creating that batch will be just one. Time will be just one. So I'm creating a little 1 by 1 tensor, and it's holding a 0. And the b type, the data type is integer. So 0 is going to be the generation. And remember that 0 is the element assigned for a new number. So it's kind of a reasonable thing to feed in the very first character in sequence to the real. So it's going to be IDX, which we're going to feed in.
He didn't pad with a weird.
Now this.
Because character models, the code is so simple because you don't need a tokenizer. So to add a token, because if all the symbols show up, I mean, you could try to find a symbol that doesn't. Whatever.
And then that gives us a type steps, which is one array of multiplices, which we have to simplify models for type tensor. So that will move on perfectly and convert those features to it. So only bring it back, we generate under tokens from and here generation ID. So obviously it's large, and using is large, this is going very well. So that's not really like train style. One thing I want to mention is this function is very integral, but it's kind of like ridiculous right now because we're feeding in all this, we're building out this context, and we're concatenating it all, and we're only feeding all 51. But that's kind of ridiculous because this is just a binary model. So we make, for example, this prediction of k. We only need this value. But actually, we define the model to the time series, and then we only look at the very last space and the rate k. So the only reason I'm writing it this way is because right now it's a binary model. But I like to keep this function fixed, and I like it to work later when our characters actually basically look further in history. And so right now history is not useful, so it's so eventually the history will be useful. And so that's why I want to just the model. So now we see that this is permanent. So let's train the model to represent the cluster. Okay, let's now train the model. So first, we have to create a total optimization object. So here we are using optimizer pattern W.
Should we try? So wait, we're using Relu now, and we want to use So here's the model. And what are we doing? We got Relu, and we are using, yeah, where's our opt state? Atom, what's the difference between Atom and Atom W? Oh, that's, and it's all deprecated? That's silly. Oh. Let's just do Atom W and see what happens. And we commented out this this loss decay. Wait, can we just fucking... Whoa. The fuck happened? I just do Atom. But if I just change this to Descent, then it works. What? Wait, oh no, it's gotta be something up here. What happened? I think what you gotta do is you gotta come back up here and try to fucking... What? Why is Atom W broken? What if I just change it to Atom? What the frick, bro? Okay, so we're not gonna use Atom because that's clearly fricked up. Okay.
I use Atom just as a optimizer and was streaming for quick second very rate from 2 million for but for very small process that is here. You can get much higher rates. 1 million 3 million higher property. But let me pick up my structure, which will just the gradients and big manage is the gradients. And then here, for access that was for. So let me actually use something that's equal to. And then number of steps. We are setting much data where value was where zero not gradients with stuff, getting the gradients of all the parameters, and then using the gradients to update parameters. So typically can do it as we saw in the series. So let me now run this for sake of demonstration. So let's look at that. So we have 3.6. Okay. What we got 3. Let's just do 10,000. And then from here we want to copy this and hopefully that will get things look like what's not and hopefully we're talking something. So now we're about to put 5-ish. So yeah. Okay. But now we're certainly going to be back here. So we're just going to base on the focus. Okay, so we see that we're starting to get something reasonable-ish.
I mean, that's pretty sick. Just the bigram model does all that, man. That's pretty sweet.
So it's difficult to be able to remember it, but be a switch. And I'm doing this because I just want to simplify opportunity work just about a button as well. So in here, I can build parameters of time. I use the few parameters that we will. Otherwise, a lot of should be parameters. Better feasibility, the data, get the sort of deeper, create the creative steps. Use the kind of data loader that gets a dash of the inputs and parameters. this is new. Now, this is the environment. Okay, forward, we also agency loss, and then here, we are in optimizer, and this is training. So every video should look equal. Now, some of the small things that happen. Number one, I had a GPU to run on a GPU in the future. So if you have a GPU, this will use speed up instead of CPU, and everything will be a lot more faster. Now, when the device turns speed up, we need to make sure that when we load the data, we move it to the device. When we create a model, we want to move a lot of parameters to the device. So as an example, we recommend that.
All right, let's do that now. Okay, so we gotta do add CUDA, cuDNN. This is gonna take a buttload of space, but I'm down to fucking try it. Let's see if it works though, because the drivers that I have are my. Here's the CUDA runtime. Yeah, fast internet. Should be no problem. I mean, we're done with this one. This one. Batch norm. Okay, so device is callable. That's what you do. You do device is callable. You move the data to this is the forward. And then you move it to CPU. Maybe it's because I didn't provide this parameter, but I feel like that makes no sense. Why would it be? Why would they do that? In any case, we gotta wait. Okay. Okay. Let's just keep watching.
And so if I were to change is I have a stable expression, and because the loss basically then goes up here, and I could use our loss with multiple times. So we take over the period, not your plants. We're going to basically get our loss, and then we're going to get the average loss for both splits. It's going to be a lot less splits. So here we're going to get the loss, we're going to report the accurate trade the knowledge splits. Now when you come back up, you notice a few things. We say the knowledge of the knowledge phase, and now here I'm resetting that to training phase. Now our model is like that. Because the main thing is in model is this, and then this network will be the same. We're going to get regional, we have both our links to the national system. but it's good practice to think through what mode we want to because some layers will have different people.
Yeah, right. I forgot. We do need to go over the batch norm.
So right now, script is about well, and that's how I started. I'm told I'm going to now running the script. It does help and most of this. Because you test my random script, restricting tree loss and power loss, you'll see that we can work somewhere around 2.5 for the figure out. And here's the second one piece. And so we have to map that script and learn the position of grades. Okay, so we're almost ready to start writing our very first subdivision block for processing these objects. Now, if we're going to get there, I would get you used to a mathematical track that is used in the subdivision inside the Torah, and it's really just at the heart of the coefficient of rotation of the subdivision. And so I would work with this.
Why the fuck is it doing this?
So let's create a debug by where BTSC is 4 equal to this data. And these are just channels, and we have patches, and we have time component, and we have some information at each point in the sequence. So now what we do is we divide these tokens. So we have up to 8 tokens here in the batch. These 8 tokens.
Okay, well it seems fine. I don't know what the hell that's about. I want to Right, so what we're gonna do, so we're gonna come down here. We are gonna add benchmark tools as well. Oh my god, like that's what I'm saying, bro. Why is that happening to me? Oh, it's the worst. Circular dependency detected. Why is it closed then? Close it when it's fixed. Come on, guys. What the hell? See, this innocent guy is getting... I'm the innocent guy. I'm getting slammed by this stupid fucking bug. Alright, so fuck it. Fuck it. Crash. Just crash. Just crash. There we go. Come on. Crash. There we go. Alright, so we're not doing the GPU today. There's fucking bugs in this weak-ass ecosystem of this failing language. Okay. Just make sure everything's compiled. God, that's so stupid. Why is everything always broken, man? Come on. What about Rust GPU? You know what? I don't even care. I just want to do this.
And in particular, we want to call them very specifically. So the token, for example, the fifth location.
Wait, we went too fast.
And then here's the second one piece. And so we're pretty much done, and we're in the position of grades. Okay, so we are almost ready to start writing our very first subdivision block for processing these objects. Now, before we actually get there, I would get you used to a mathematical trick that is used in the subdivision inside the Torah, and it's really just at the heart of the coefficient of rotation of the subdivision. And so I want to work with this example, which is used for the operation, and then it's going to make it much more clear once we actually get to it in the script. So let's create a b by t by c, where b, t, and c are just 4, 8, and 2 in the straight set. And these are basically channels, and we have batches, And we have a time component, and we have some information at each point in the sequence. So C. Now, what we would like to do is we would like these tokens. So we have up to 8 tokens here in a batch. And these 8 tokens are currently not talking to each other, and we like them to talk to each other. We like to couple them. And in particular, we want to couple them in a very specific way. So the token, for example, the 5th location, it should not communicate with tokens in the 6th, 7th, and 8th location, because those are future tokens in the sequence. The token on the 5th location should only talk to the other one in the 4th, 3rd, 2nd, and 1st. So information only flows from previous context to the current timestamp. And we cannot get any information from the future because we are about to try to predict the future. So what is the easiest way for tokens to communicate? Okay, easiest way I would say is, okay, we're a 5th token, and I'd like to communicate with my past. The simplest way we can do that is to just do an average of all the preceding ones. So, for example, if I'm a 5th token, I would like to take the channels that make up that information of my step, but then also the channels from 4th step, 3rd step, 2nd step, and 1st step. I'd like to average those up, and then that will become sort of like a feature vector that summarizes me in the context of my history. Now, of course, just doing a sum or like an average is an extremely weak form of interaction. But this communication was extremely lost. We lost a ton of information when spatial arrangements of all those tokens. But that's okay for now. We'll see how we can bring that information back later. For now, what we'd like to do is, for every single batch element in the boundary, for every teeth token in that sequence, we'd like to now calculate the average of all the vectors in all the previous tokens and also at this token. So let's write that out.
Why?
Let me just copy this thing. So in other words, we're going to create X. W is equal to backwards. Because backwards is kind of like a term people use when you're just averaging out things. So it's just backwards. Basically, there's a word stored on every one of these equal digits, and we have to do it backwards. So we're going to say that it's just different to it. And then I'm using a formula here, so not to mention it, that's coming. But for now, we're just iterating over all the batch methods. Iterating over time. And then the previous tokens are at this batch of measure, and then everything up to and including the teeth token. Okay. So when we slice out X in this way, X spread becomes of shape, how many teeth elements there are in the past, and then of course C, so all the two-dimensional information from these little tokens. So that's the previous sort of chunk of tokens from my current sequence. And then I'm just doing the average, or the mean, over the 0th dimension. So I'm averaging out the time. And I'm just going to get a little C one-dimensional vector, which I'm going to store in X backwards. So I can run this, and this is not going to be very informative because, let's see, so this is X of 0, so this is the 0 batch point, and then X at 0. Now, you see how the first location here, you see that the two are equal. And that's because it's, we're just doing average of these 1, 2. But here, this one is now an average of these 2. And now this one is an average of these 3. And so.
Okay, I still don't get it. So, like, what's the point?
The tokens now gives this one. So this is all well and good, but this is very inefficient. Now the trick is that we can be very, very efficient about doing this using matrix multiplication. So that's the mathematical trick. Let me show you what I mean. Let's work with the toy example. I have a simple matrix here that is 3 by 3 of all ones. Make it 3 by 3 and it's a 3 by 2. And make C, which will be 3 by 3 multiplied 3 by 2, which will give out 3 by 2. So here we're just using matrix multiplication. So A multiplied B gives us C. Okay, so how are these numbers in C achieved, right? So this number in the top left is the first row of A dot product with the first column of B. And since all the row of A right now is 1 twice, and the dot product here with this column B is just going to be the sum of this column. So 2 plus 6 plus 6 is 14. The element here, the element C, is also the first column here, the first row of A, multiplied now with the second column of B. So 7 plus 4 plus 5 is 16. Now you see that there's repeating elements. So this 14 again is because this row is again all ones, and it's multiplying the first column of B. So
Oh, and then you just mask. This trick is, it's just a bunch of malarkey, bro. They try to make it sound more complicated than it is. He's just gonna mask it.
Which is short for triangular, something like that. And you can wrap it in push up less.
Triangle or something like that.
So now it will basically 0. So we just get the little triangle.
Wait, how do I get a lower? Oh, fuck. Wait, what happened? Did something fail? Okay, hold on. Julia, lower triangular. How do I generate? How do I make one? There's gotta be a... Is there a trill? Triangular lower? Ooh. Whoa, what happened there? All right, let's look at the generated uh yeah, pretty good loss. God, I love that picture. It's so pretty for some reason. Okay, the batch room. I don't really care about the batch room, but what I care about is oh yeah, trill. Okay. Let's do a using because I don't know if I have a using in my all right. So what is this trill? All right, nice. Wait. Lower triangle of a matrix. All right, so I guess we do trill ones 4x4. No, but see that's oh wait, hold on. Yeah. Um Wait, does it take a T? No, so I'd have to do. Oh wait, what if I do a true? Wait, no. Sorry. Wait, actually, that's interesting. What if I do ones bool? What happens there? There's that. But then what if I do trues? I think it's this. I think it's literally the same thing. Oh no, but see, this returns a bit matrix. See, that's fast. See, okay, that's probably what I want to do. A bit matrix. Because that's really a mask. Because if we do the size of this, so let's do the B. How do I get the size of? Size in bytes of A. 16. Size of B. 8. Why is it 8? There must be some... Because what's the size of a true? A byte? So then why is this 8? I guess they has to store some dimension information or something. I don't know. I mean, that's pretty sick. I like this.
These elements here are not ignored, so we just get a 2. And then this number here is the first row of the second row. And because these are zeros, they get ignored, so it's just 7. The 7 plus 12. A little bit happened here, because this is 1 and then zeros, what ended up happening is we're just blocking out this row, and that's what we got. Now here, we have 1, 1, 0. So here, 1, 1, 0 dot product with these two columns, so now we have 7 plus 6, which is 8, and 7 plus 4, which is 11.
So what do you do after that? You divide by the index.
And so basically, how many rows, right? So the row is 1, this row is put back 0.
A divided by torch dash oh. Oh, that's how you do it? That's silly. Okay.
And now we do A multiply B. What are we getting? Here we are just getting the first row. Here now we are getting the
I guess that's the same.
first two rows. And so
But wait, but it feels like this has more moles than you technically need. Like this seems not optimal, but because like you shouldn't have to do this 0.3, 0.3, you should have to just do one div. Whatever.
and on the bottom here, we're now getting the average of my manipulator can do and weights. It's just from 3D.
Okay, so let's just do this. So we got here, let's do. So what is it? It's gonna be, well, this is gonna be this is gonna be this. So we got this. Wait, let's make it 3 by 3. Okay. Then b is equal to rand uh 1 to 10 3 by 3. Oh wait, 3 by 2, right? Okay, cool. But now, so wait, so we get the 5 by 2, we get the 15. But so now what I would say is you want to divide each row by 1, 2, size of C2. Or C1, sorry. C1. Yeah. And this is going to be, so how do you want to do this? You want to, C dot divided by this. Wait, I think we need to do this. Right, so it's 5 by 2, then 7.5. Is that right? Yeah, see, I feel like this is faster. Um, you can't get each index along a dimension. Axes for valid indices along one dimension. Okay, so we want axes of C1. That's what we want. There we go. I'm just doing friggin' optimization, bro. This, okay, wait, because if we do a B time on this, 17 nanoseconds, 1 allocation. I feel like that's not even an allocation, actually. But then we want to do this. What did we have before? 69 nanoseconds. I mean, that's a fast freaking operation. I think it's dominated by allocation time. But I feel like that's got to be faster than then how do you do it? How did he generate this? Well, you have to do. All right, I don't care.
Using the so we are going to produce an array A. Up here I'm going to put a wing short for weights. But this is our A. And this is how much of every row we want to average up. And it's going to be an average because you can see that these rows sum to 1. So this is our A. And then our B in this example, of course, is X. So what's going to happen here now is that we're going to have an exponent 2. And this exponent 2 is going to be way multiplying Rx. So let's think this through. Way is T by T. And this is matrix multiplying and E by T by C. And it's giving us what shape. So backwards multiplying, you'll see that these shapes are not the same. So it will create a dash dimension here. And this is a dash matrix multiplier. And so it will apply this matrix multiplication all the batch elements in parallel and individually. And then for each batch element, there will be a T by T multiplying T by C, exactly as we have below. So this will now create B by T by C and X star 2.
Is that gonna work? I don't know how to do that in Julia.
So we can see that torque dot outputs of X bar and X bar 2 should be true. Now, so this kind of like convinces us that these are in fact the same. So Expo and Expo 2, I just print them. Okay, we're not gonna be able to. Okay, we're not gonna be able to stare it down, but well, let me try Expo. This is just at the 0th element, and Expo 2 at the 0th element. So just the first batch. We should see that this and that should be identical, which they are. Right? So what happened here? The trick is we were able to use batch matrix multiplying to do this aggregation here. And it's a weighted aggregation. And the weights are specified as T by T array. And basically weighted sums. And these weighted sums are according to the weights inside here that take on sort of this triangular form. And so that means that every dimension will only get some information from the
Oh, but you learn how to You learn how to weight them? Ah, that's crazy, bro.
So this is the third
Is that real?
of the process.
That's silly, man.
It uses softmax.
I feel like the story of this whole AI thing is you just gotta like, you gotta be smart and allow it to learn. You gotta allow it to learn. Otherwise, most of the time you're just crippling its ability to learn by doing math. But you have to design it in a way that allows it to. It's clever, man. It's clever.
Is this matrix. Low triangular elements. Wait, it's all zero. And so if I just break weight in the beginning, it's all zero. Then I use masked fill. So what this is doing is weight of masked fill, it's all zeros. And I'm saying for all the elements where trill is equal to zero, make them a negative infinity. So all the elements where trill is zero will become negative infinity. So this is what we get. And then the final one here is softmax. So if I take a softmax along every single, so dim is negative one, so along every single row, if I do a softmax, what is that going to do? Well, softmax is also like a normalization operation, right? And so spoiler alert, I can get the exact same matrix. Let me bring back to softmax. And recall that in softmax, we're going to exponentiate every single one of these, and then we're going to divide by the sum. And so if we exponentiate every single element here, we're going to get a 1, and here we're going to get basically 0, 0, 0, 0, everything else. And then when we normalize, we're just going to here we're going to get 1, 1, and then 0.
Oh, but softmax has the div in it. I don't know. I don't care about the performance, bro. I really don't. Not at the moment.
And the reason we're using self-attention is that these weights here begin with 0. And you can think of this as like an interaction string, or like an affinity. So basically, it's telling us how much of each token from the past do we want to aggregate and average up. And then this line is saying tokens from the past cannot communicate. By setting them to negative infinity, we're saying that we will not aggregate anything from those tokens. And so basically, this then goes for softmax into the weighted, and this is the aggregation through matrix multiplication. And so this is that. You can think of these as these zeros are currently just set by s to be 0, but a quick preview is that these affinities between the tokens are not going to be just constant at 0. They're going to be data dependent. These tokens are going to start looking at each other, and some tokens will find other tokens more or less interesting. And depending on what their values are, they're going to find each other interesting to different amounts, and I'm going to call those affinities. And then here we are saying, we just want to communicate the past. We're going to plan them. And then when we normalize and sum, we're going to aggregate sort of their values depending on how interesting we find each other. And so that's the preview for self-attention. And basically, long story short from this entire section is that you can do weighted aggregations of your past elements by using matrix multiplication of a lower triangular fashion. And then the elements here in the lower triangular part are telling you how much of each element fuses into this position. So we're going to use this trick now to develop a self-attention block. So first, let's get some quick preliminaries out of the way. First, the thing I'm kind of bothered by is that see how we're passing in vocab size into the constructor? There's no need to do that because vocab size is already defined up top as a weighted variable. So there's no need to pass this stuff around. Next thing I want to do is I don't want to actually create, I want to create like a level of introduction here where we don't directly go to the embedding for the widgets, but instead we go through this intermediate phase because we're going to start making that bigger. So let me introduce a new variable, an embed. It's short for number of embedding dimensions. So an embed here will be saying 32. That was a suggestion from GitHub Copilot, by the way. It also suggests 32, which is a good number. So this is an embedding table and only 32 dimensional embeddings. So then here, this is not going to give us logits rep. Instead, it's going to give us token embeddings. So I'm going to call it. And then to go from the token embeddings to the logits, we're going to need a linear layer. So sub.lm, let's call it, short for language model 1, is any linear from an embed up to vocab size. And then when we swing over here, we're actually going to get the logits by.
Bro, I gotta get Copilot again. This is stupid. Why am I not fucking using this?
This is an embed C, and this is vocab size. So let's just say that an embed is equal to C. And then this just creates one spurious layer of introduction through a linear layer, but this should basically be. So we see that it starts, and this currently was kind of spurious, but we're going to build on top of this. Next up, so far we've taken these indices and we've encoded them based on the identity of the tokens inside IDX. The next thing that people very often do is that we're not just encoding the identity of these tokens, but also their position. So we're going to have a second position embedding table. So self.position embedding table is an embedding of block size by embedding. And so each position from 0 to block size -1 will also get its own embedding metric. And then here, first let me decode b by t from idx.shape. And then here, we're also going to have a plus embedding, which is the positional embedding, and this is turned range. So this will be basically just integers from 0 to t minus 1. And all of those integers from 0 to t minus 1 get embedded through the table to create a t by c. And then here, this gets renamed to just say x. And x will be the addition of the token embeddings with the positional embeddings. And here, the broadcasting node will work out. So b by t by c plus t by c, this gets right aligned, a new dimension of 1 is added, and it gets broadcasted across batch. So at this point, x holds not just the token identities, but the positions at which these tokens occur. And this is frankly not that useful because, of course, we just have a simple binary model, so it doesn't matter if you're in fifth position, second position, or wherever. It's all translation invariant at this stage. So this information currently wouldn't help. But as we work on self-attention on, we'll see that this starts to matter. Okay, so now we get to the crux of self-attention. So this is probably the most important part of this video too. First, we're going to implement a small self-attention for a single individual head as their goal. So we start off with where we were. So all this code is familiar. So right now, I'm working with an example where I change the number of channels from 2 to 32. So we have a 4x8 arrangement of tokens. And each token, and the information of each token is currently 32 measured. But we just are working with random numbers. Now we saw here that the code as we had it before does a simple average of all the past tokens and the current token. So
I want to know, because I'm thinking ahead here, and I just want to know, how does YouTube DLP without an API key get the metadata for a YouTube video? And we want to really? It searches for specific script blocks contains. No, wait, hold on. What do we think this is? Oh, I mean, come on, dude. Come on, bro. That's so good. Okay. That's so funny that it rickrolled me. Still makes me laugh.
this information and current information should be mixed together. And that's what this code currently is. And that's by creating this low triangular structure.
Do we have a fill thing? Can we do that? No docstring, no docstring, docstring. Oh no, I think what we can do actually is wait, hold on. Okay, so we have the inverse bit matrix, and I think we could similarly do I'm on a fucking benchmarking kick right now, bro. I don't know what it is, but 79 or 75, 54. So inverting it is what we want to do here. So we want to go like this, and we want to use this to index into something, right? Way.masked fill. Oh, no, wait. Okay, wait. Does this work? Oh, that's so fucking cool, man. Inf? Oh, is it inf? That's fucking awesome, bro. Low level numerical coding. High performance.
Currently, when we initialize the affinities between all the different tokens or nodes, okay, we go to interchangeable. So when we initialize the affinities between all the different tokens to be 0, then we see that way gives us this structure where every single row has these uniform numbers. That's what then in this matrix multiply makes it something that we would pay some language. Now, we don't actually want this to be all uniform because different.
Wait, hold on. This is a B by T by C. This is out. X is 4 by 8 by 32. Fuck, dude. It's crazy how much easier it is to conceptualize a matrix than it is to conceptualize a n-dimensional array.
In my past, and maybe I want to know what those constants are, and I want that information to float. And so I want to now gather information from the past, but I want to do it in a data-dependent way. And this is the problem that self-attention solves. Now, the way self-attention solves this is the following. Every single node, or every single group at each position will emit two vectors. It will emit a query, and it will emit a key. Now, the query vector, roughly speaking, is what am I looking for? And the key vector, roughly speaking, is what do I want to do? And then the way we get the product between these tokens now in a sequence is we basically just do a dot product between the keys and the queries. So my query dot product to all the keys of all the other tokens, and that dot product now becomes weight. And so if the key and the query are they will interact very well enough, and then I will get to learn more about that particular token as opposed to any other token. So let's do this. We're going to open with a single what's called head of self-attention. So this is just one head. There's a hyperparameter of all these, which is the head size. And then here I'm initializing linear modules, and I'm using bicycle skills, so these are just going to apply matrix multiply with some fixed states. And now let me produce a key and q, k and q, by forwarding these modules on x.
So C is the channels.
B by t by 16, because that is the bit size, and the same with b by t by 16. So this being bit size. So you see here that when I forward this linear on top of my x, all the tokens in all positions in the b by t arrangement, all of them in parallel and independently produce a key and a query. So no communication will happen. Communication happens now. All the queries will interact with all the keys. So basically what we want is we want to bring now all the affinities between these to the query multiplying key. And we have to be careful with, we can't matrix multiply this. We actually need to transpose k. But we have to be also careful because these are any computational dimension. So in particular, we want to transpose the last two dimensions, dimension -1 and dimension -2. So -2, -1. And so this matrix multiply now will basically do the following. B by t by 16. Matrix multiplies b by 16 by t to give us b by t by t. Right? So for every row of b, we're now going to have a t square matrix giving us the affinities. And these are now the weight. So they're not zeros. They are not running from this dot product between the keys and the queries. So this can now run. I can now run this. And the weighted aggregation now is a function in a data manner between the keys and queries of these nodes. So just inspecting what happened here, the way takes on this form. And you see that before way was just a constant, so it was applied in the same way to all the batch elements. But now every single batch element will have different sort of way because every single batch element contains different tokens.
But there's no nonlinearity in there. I feel like you need a nonlinearity somewhere.
These are the weights that came out. As you can see now that they're not just exactly uniform. And in particular, as an example here for the last row, this was the 8th token. And the 8th token knows what content it has, and it knows kind of position. And now the 8th token, based on that, creates a query. Hey, I'm looking for this kind of stuff. I'm a vowel, I'm on the 8th position, I'm looking for any consonants at positions up to 4. And then all the nodes between the keys. And maybe one of the channels could be, I am a consonant, and I am in the position up to 4. And that key would have a high number in that position.
Oh, bro, that's so cool. That's so cool. I gotta hear him say it again.
You see that before it was applied in the same way to all the batch elements. But now every single batch element will have different sort of weight because every single batch element contains different tokens and different positions. And so this is not a different point. So when we look at just the 0 row, for example, in the input, these are the weights that came out. As you can see now that they're not just exactly uniform. In particular, as an example here for the last row, this was the 8th token. And the 8th token knows what content it has, and it knows what position it's in. And now the 8th token, based on that, creates a query. Hey, I'm looking for this kind of stuff. I'm a vowel, I'm on the 8th position, I'm looking for any consonants at positions up to 4. And then all the nodes between the keys. And maybe one of the channels could be, I am a consonant, and I am in the position up to 4. And that key would have a high number in that specific channel. And that's how the query and the key, when they dot product, they can find each other and create a high affinity. And when they had a high affinity, let's say this token was pretty interesting to this 8th token. When they have a high affinity, then through the softmax, I will end up aggregating a lot of its information into my position. And so I'll get to learn a lot about it. Now, just this, we're looking at way after this has already happened. Let me erase this operation as well. So let me erase the masking and the softmax, just to show you the underdefined internals of the works. So without the masking and the softmax, way comes out like this, right? This is the outputs of dot products. And these are the raw outputs, and they take our values from -2 to +2, etc. So that's the raw interactions, the raw affinities between all the nodes. But now, if I'm a fifth node, I will not want to aggregate anything from the sixth node, seventh node, and the eighth node. So actually, we use the upper triangular masking. So those are not allowed to communicate. And now we actually want to have a nice distribution. So we don't want to aggregate negative 0.11 of this node, that's crazy. So instead we exponentiate and normalize. And now we get a nice distribution that's 61. And this is telling us now that it doesn't matter how much information to aggregate from any of these tokens in the past. So that's ready. It's not zero sum anymore. It's not in this way. Now there's one more part to a single self-adjusting head. And that is that when we do the aggregation, we don't actually aggregate the tokens exactly. We produce one more value here, and we call that the value. So in a single head, we produce key and array, we're also going to create a value. And then here, we don't aggregate x. We calculate a b, which is just achieved by propagating this linear on top of x again. And then we calculate the way so b is the element that aggregate the losses. And now, of course, this will make it so that output here of the single head will be 16 dimensional because that is the head size. So you can think of x as kind of like private information to this, if you think about it that way. So x is kind of private to this token. So I'm a fifth token, that's an ISO identity, and my information is kept in vector x. And now, for the purposes of a single head, here's what I'm interested in, here's what I have, and if you find me interesting, here's what I will communicate to you. And that's stored in b. And so b is the thing that gets aggregated for the purposes of this single head between the different nodes. And that's basically the self-adjustion mechanism. This is what it does. There are a few notes that I would like to make about.
It seems so arbitrary, bro. Like,
It's a communication mechanism. You can really think about it as a communication mechanism where you have a number of nodes in a directed graph, where basically you have edges pointing between nodes like this. And what happens is every node has some vector of information, and I guess you aggregate information via a weighted sum from all the nodes that point to it. And this is done in a data-dependent manner, so depending on whatever data is actually stored in each node at any point in time. Now, our graph doesn't look like this. Our graph has a different structure. We have 8 nodes because the block has a state, and there's always 8 tokens. And the first node is only pointed to by itself. The second node is pointed to by the first node and itself, all the way up to the 8th node, which is pointed to by all the previous nodes and itself. And so that's the structure that our directed graph has, happens to have in auto-regressive, so a scenario like language level. But in principle, it actually can be applied to any arbitrary directed graph. And it's just a communication mechanism.
Is a lower triangular matrix literally just that graph? Dude, we... do we want graph plots? I feel like I'm going down a rabbit hole. But okay, wait, let's just look at okay, let's just look at the A. So in this case, so an asymmetric matrix is going to be a directed graph. This is node 1 is connected to node 1, node 2 is connected to node 2, node 3 is connected to node 2. Now, node 2 is connected to node 1. Node 3 is connected to node 1. So we probably want to do the because what we want is 1 is connected to 2, 1 is connected to 3, 2 is connected to 3. Alright, I don't need to plot the graph. I'm pretty sure that this is what that graph is.
So potential simply acts over like the separate vectors in the graph. And so by default, these nodes have no idea where they are positioned in space. And that's why we need to encode them positionally and sort of give them some information that's anchored to a specific position so that they sort of know where they are. And this is different than, for example, from convolution. Because if you run, for example, a convolution operation of a input, there's a very specific sort of layout of the information in space, and the convolutional filters sort of act in space. And so it's not like intuition. Intuition is just a set of vectors out there in space and communicate. And if you want them to have a notion of space, you need to specifically add it, which is what we've done when we calculate relative the positional encodings and added that information to the vectors. The next thing that I hope is very clear is that the elements across the batch dimension, which are independent examples, never talk to each other. They're always processed independently. And this is a batch matrix multiply that applies basically a matrix multiplication kind of in parallel across the batch dimension. So maybe it would be more accurate to say that in this analogy of a directed graph, we really have, because the batch size is 4, we really have 4 separate pools of 8 nodes. And those 8 nodes only talk to each other. Until there's about 32 nodes that are being processed. But there's sort of 4 separate.
Okay, so he's making it sound, I feel like he's making it sound complicated, but I think he's talking in contrast to batch norm, which couples examples in a batch. This is not.
Next note is that here in the case of language modeling, we have a specific structure of directed graph where the future tokens will not communicate to the past tokens. This doesn't necessarily have to be the constraint in a general case. And in fact, in many cases, you may want to have all of the nodes talk to each other fully. So, for example, if you're doing sentiment analysis or something like that with a transformer, you might have number tokens, and you may want to have them all talk to each other fully, because later you are predicting, for example, the sentiment of the sentence. And so it's okay for these nodes to talk to each other. And so in those cases, you will use an encoded block of self-attention. And all of these that encoded block is that you will delete this line code, allowing every node to correctly talk. What we're implementing here is sometimes called the decoded block. And it's called a decoder because it's sort of a decoding language, and it's got this autoregressive format where you have to mask the triangular matrix so that most of the future never talk to.
Bro, these nerds, these freaking nerds make it sound so complicated. Not Andrej. I love Andrej. He's freaking bad Mephisto. He can never do anything wrong.
The next thing I wanted to comment on is you keep hearing me say attention, self-attention, etc. There's actually also something called cross-attention. What is the difference? So basically, the reason this attention is self-attention is because the keys, queries, and the values are all coming from the same source from X. So the same source X produces keys, queries, and values. So these nodes are self-attentive. In principle, attention is much more general than that. So for example, in encoded decoder transformers, you can have a case where the queries are produced from X, but the keys and the values come from a whole separate external source, and sometimes from encoded blocks that encode some context that we lack a condition on. And so the keys and the values will actually come from a whole separate source. Those are nodes on the side, and here we're just producing queries, and we're reading up information from the side. So cross-attention is used when there's a separate source of nodes we might be pull information from into our nodes. And it's self-attention if we just have nodes that we have to look at each other to talk to each other. So this attention here happens to be self-attention. But in principle, attention is not much more. Okay, and the last note at this stage is if we talk about the
I am curious though, if I just do, hold on. I am curious though, if I just do simple digraph of A. Nice. Right, 1 is connected to 1, 2 is connected to 1, 2 is connected to 2, 3 is connected to 1, 3 is connected to 2, 3 is connected to 3. Wait, hold on. But there's no 1 to 3. Yeah, so what we actually want is 1 is connected to 2, 1 is connected to 3, 2 is connected. All right, so there we go. So we did that thing. Easy, bro.
We've already implemented attention. So given query key and value, we've multiplied the query and the key, we've softmaxed it, and then we are aggregating the values. There's one more thing that we're missing here, which is we're dividing by 1 over square root of the head size, the data to the head size. Why are we doing this by simple? So APON is 1 attention. And it's kind of like an important normalization case with math. The problem is if you have unit Gaussian inputs, so 0 meaning variance, K and Q are unit Gaussian, and if you just do weight immediately, then you see that your weight actually will be, the variance will be on the order of head size, which in our case is 16.
See, again, I never read any of these papers, but this demystifies so much stuff.
And the variance of weight will be 1, so we preserve. Now, simple. You notice that weight here will feed into softmax. And so it's really important, especially if it's Chelsea, that weight fairly diffuse. So in our case here, it's sort of blacked out here, and weight at fairly diffuse numbers here. So like this. Now the problem is that because of softmax, if weight takes on very positive and very negative numbers inside of it, softmax will actually converge towards one-hot vectors. And so I can illustrate that here. Say we are applying softmax to a tensor of values that are very close to 0, then we're going to get diffuse in out of softmax. But the moment I take the exact same thing and I start sharpening it, making it bigger by multiplying these numbers to 8, for example, you'll see that the softmax will start to sharpen. And in fact, it will sharpen towards the max. So it will sharpen towards whatever number to it is.
Oh, interesting. You know, that reminds me of how you can find an eigenvector by repeatedly squaring a matrix. Like if you repeatedly square a matrix, like let's just take m is equal to rand 3 by 3 or rand n 3 by 3, and we wanted to find the eigenvectors of this. I think we could do like base.power by squaring m 10, and I think that if you keep going, you'll be able to. It basically creates an ellipsoid. Let's make it 2 by 2. You basically create an ellipsoid that well, let's see. Eigenvector by squaring. Anyways, I'm pretty sure that you can, let's just see. you approximate a eigenvector by repeatedly squaring the matrix. Oh, right. You don't find all of them. You find the largest one. Tends to align with the vector of the eigenvector corresponding to lambda max. Yeah, I feel like that's. I don't know why that reminds me of the same thing, but it reminds me of the same thing.
You're basically aggregating information from a single node. Every node just aggregates information from a single other node. It's not only one, especially with initialization. And so the scaling is used just to control the variance at initialization. Okay, so having said all that, let's now take our self-attention knowledge and let's take a process. So here in the code, I created this head module and implements a single head of self-attention. So you give it a head size, and then here it creates the key, hurry, and the value linear layers. Typically, people don't use biases for this. So those are the linear projections that we're going to apply to all of our nodes. Now here.
See, okay, now what I'm curious about is how in Flux do you set that up? Because in Flux, it's a chain, it's a linear, it's not a DAG. It's not a compute DAG. Wait. Let me read the docstring. Chain layers. Collects multiple layers functions to be called in a sequence on a given input. Supports slicing. Oh, cool. And you can give it a name. Oh, that's nice. So it's like a quarg thing. But and here's literally just a function. Uh-huh. Oh, that's nice. See, I was doing dot layers, but you can just index it like normal. That's nice. That's nice because you want that. Is there an inverse tan H? Uh, what? A chain may be called with multiple arguments. What? I do not understand what parallel means. For large models, there's a special type unstable path which. Okay. So I don't know how you do something like this because I guess what you would do is you would just manually manage the matrix, but you wouldn't do it with dense. I think there's probably a, let's see, flux.attention. Where are the NN? No, it's not an NN and lib. Where do all these things live? Where's the docs? Did I close the docs? In any case, cut layers. He said it's called attention, right? Built-in layers. Here you go. Dense, bilinear. I've never even heard of that. Multi-head attention. Where's single-head attention? They only have one. I guess you just. The basic blocks need to implement transform architecture. See this functional. Okay, so there's a. Alright, so why don't we, so let's just say, yeah, flux, or let's just say attention. Okay, can still do this. And then there's also, I feel like I just want to derive. What the hell does this even do? It doesn't even open up any. There we go. Where's the source code, though? So it's a struct that's presumably callable. Oh, and then there's a macro layer. Okay. See, oh, so, okay, so you just manually do this. The Q, the K, the V. Alright. I'll be right back. Okay. There's A3. That just means it's a three-dimensional array. Oh, there you go.
Fill is not a parameter of the module, so in sort of hyper-training conditions, this is called the buffer. It's not a parameter, and you have to call it. You have to assign it to an object using a register buffer. So that creates the triangle matrix. And then we're giving the index. This should be correct now. We got the key. It works. We calculate the attention scores this that way. We normalize it so we can scale protection form. Then we make sure that picture doesn't move in the past, so this makes it being encoded wrong. And then softmax, and then aggregate value. And here, we're model on creating a head in the constructor and calling it self-protection head. And the head size, we're going to keep the same anyway, just for now. And then here, once we've encoded the information with the token embeddings and the position embeddings, we're simply going to feed it self-protection. And then here, once we've encoded the information with the token embeddings and the position, just for now.
Try to pause it.
And then here, once we've encoded the information with the token embeddings, we're simply going to feed it self-protection head. And then the output of that is going to go into the decoder, language model head, and create the weights. This is sort of the simplest way to plug in a self-protection input into our network right now. I have to make another thing, which is that here, in the generate, we have to make sure that our IDX that we feed into the model, because now we use position embeddings, we can never have more than block size at the end. Because if IDX is more than block size, then our position embedding table is going to run out of scope because it only has embeddings for up to block size. And so therefore I added some context that we're going to feed into self.
I was wondering about that.
So those are the changes, and we're going to start treating it. So I also came up with a script here, and I increased the learning rate because the self-protection can't tolerate very low rates. And then I also made these number of iterations to learn rates lower. And then I trained it, and previously we were only able to get to 2.5, and now we are about to 2.4. So we definitely see a little bit of improvement. From 2.5 to 2.4 roughly, the text is still not finished. So clearly the self-protection has been some useful communication, but we still have a okay, so now it's still not our attention. Now next, maybe we should install in the paper, there's something called multi-attention. And what's multi-attention? It's just applying multiple attentions in parallel and concatenating the results. So we have a little bit bad right here. I don't know if this is super clear. It's really just multiple attentions in parallel. So let's implement that. Fairly straightforward. If we want a multi-head attention, then we'll multi-head attention running in parallel. So in PyTorch, we can do this by simply creating multiple heads. So however many heads you want, and then 5. And then we run all of them in parallel into a list, and we concatenate all of the buckets. And we're concatenating into the channel dimension. So the way this looks now is we don't have just a single attention that has a hit size of 32, because remember, an event is 32. Instead of having one communication channel, we now have 4 communication channels in parallel. And each one of these communication channels typically will be smaller correspondingly. So because we have 4 communication channels, we want 8-dimensional sections. And so for each communication channel, we're putting together 8-dimensional vectors, and then we have 4 of them, and that concatenates to give us 32, which is the original event. And so this is kind of similar to, if you're familiar with convolutions, this is kind of like a group convolution, because basically, instead of having one large convolution, we do convolution groups, and that's multi-headed self-protection. And so then here, we just use same heads, self-protection heads instead. Now, I actually ran it, and I ran the same thing, and then we now get down to 2.28. And the output is still, the generation is still not amazing, but clearly the value for us is improving, because we were at 2.4 just now. And so it helps to have multiple communication channels, because obviously these tokens have a lot to talk about. They want to find consonants, the vowels, they want to find the vowels from certain positions, they want to find any other different things. And so it helps to create multiple independent channels of communication, gather lots of different types of data, and then decode the data. Now going back to the data for a second, of course I didn't explain this figure in detail. We are starting to see something present will be already implemented. We have the positional encodings, helpful encodings that add, we have the masked multi-headed attention implemented. Now, here's another multi-headed attention, which is a cross attention to an encode, which we're not going to implement in this case. I'm going to come back to that later. But I want you to notice that there's a feed-forward part here, and then this is grouped into a block that is repeated again and again. Now, the feed-forward part here is just a simple multi-layer abstraction. So here position when I speak forward networks is just a simple ML. So I want to start this in a similar fashion, also adding computation into the network. And this computation is on a per node level. So I've already implemented it. We can see the div on the left here when I've added and changed things. Now before we had the multi-headed self-attention that did the communication, but we went way too fast to calculate the limits. So the papers looked at each other, but they didn't have a lot of time to think on what they found from the other papers. And so what I put here is a little feed-forward single layer, and the little layer is just a layer followed by a really long layer, and that's it. So it's just a little layer, and then I call it feed-forward, and then that, and then this feed-forward is just one sequentially right after forward, and then that, and then this feed-forward is just one sequentially right after the self-attention. So we self-attend, and we feed-forward. In the mode that the feed-forward trying to find over, this is on the first one. All the code will be independent. So the self-attention is the communication, and then once they gather the data, now they need to think on that data individually. And so that's what people would do, and that's
interesting.
And so as a preview, the communication with the computation, and that's also what the transformer does. When it comes along, and then repeat, and it groups them, and it groups. So let me tell you what we like. We'd like to do something like this. We have a block, and this block is basically this part here, except for the cross attention. The block basically intersperses communication and the computation. The computation is done using multi-headed self-attention, and then the computation is done using a feed-forward map, and all the tokens together. Now, what I've added here also is you'll notice this states the number of embeddings in the embedding dimension and the number of heads that we would like, which is kind of like group size in group calculation. And I'm saying that the number of heads we'd like is 4. And so because this is 32, we calculate that because this is 32, the number of heads should be 4, the head size should be 8, so that everything sort of works out channelized. So this is how the transformer structures, so the sizes typically. So the head size will become 8, and then this is how we're going to intersperse them. And then here, I'm trying to create blocks, which is just a sequential computation of block, block, block. So then we're interspersing communication feed-forward many times, and then finally we decode. Now, I actually tried to run this, and the problem is this doesn't actually give a very good answer, and a very good result. And the reason for that is we're starting to actually get like a deep neural net. And deep neural nets self-optimization issues, and I think that's what we're kind of like starting to run into. So we need one more idea that we can borrow from the transformer paper to resolve the difficulties. Now, there are two optimizations that dramatically help with the depth of these networks and make sure that the networks remain optimized. Let's talk about the first one. The first one in this diagram is you see this arrow here, and then this arrow and this arrow. Those are stick connections, or sometimes called residual connections. They come from this paper, the Residual Learning Formula Definition, from about 2015, that introduced the concept. Now, these are basically, what it means is in transformed data, but then you have a stick connection with addition from previous features. Now, the way I like to visualize it, that I prefer, is the following. Here the computation happens from the top to bottom, and basically you have this residual pathway, and you are free to fork off from the residual pathway, perform some computation, and then project back to the residual pathway via addition. And so you go from the inputs to the targets only via plus and plus and plus. And the reason this is useful is because during backpropagation, remember from our micrograph video earlier, addition distributes gradients equally to both of its branches that is the input. And so the supervision or the gradients from the loss basically hop through every addition node all the way to the input, and then also fork off into the residual nodes. But basically, you have this gradient superhighway that goes right from the supervision all the way to the input, unimpeded.
Gradient superhighway. Okay.
So they contribute very, very little, if anything, to the residual pathway. They are initialized that way. So in the beginning, they are sort of almost kind of like not there. But then during the optimization, they come online over time, and they start to contribute about at least at the initialization. You can go from directly supervision to the input, gradient is unimpeded and disclosed, and then the blocks over time kick in. And so that dramatically helps with the optimization. So let's look at this. So coming back to our block here, basically what we want to do is we want to do x equals x plus self-attention and x equals x plus self-activity. So this is x, and then we fork off and do some communication and come back. And we fork off and do some computation and come back. So those are residual connections. And then swinging back up here, we also have to introduce this projection. So nn.linear, and this is going to be from actually compressing this. This is size n. So this is the output of the self-attention itself. But then we actually want the two-part projection, and that's the result. So the projection is just a linear transformation of the outcome of this thing. So that's the projection back into the residual pathway. And then here in the feed-forward, it's going to be the same thing. I can have a self-projection here as well, but let me just simplify it, and let me coupled inside the same sequential container. And so this is the projection layer going back into the residual packet. And so that's it. So now we can print. So I'm implementing one more small change. When you look into the paper again, you see that the dimensionality of input and output is factoral for them. And they're saying that the inner layer here in the feed forward has a dimensionality of 2048. So there's a multiplier of 4. And so the inner layer of the feed forward network should be multiplied by 4 in terms of channel sizes. So I came here and I multiplied 4 times embed here for the feed forward, and then from 4 times n embed going back down to embed when we go back to the projection. So adding a bit of computation here and growing that layer that is the residual block on the side of the residual block. And then I train this, and we actually get down all the way to 2.08 validation loss. We also see that the network is starting to get big enough that our train loss is getting ahead of validation loss. So we start to see like a really big. And our generations here are still not amazing, but at least you see that we can see like is here, this now, read, send. Like this starts to almost look like English. So yeah, we're starting to really get there. Okay, and the second accumulation that is very helpful for optimizing your deep neural networks is right here. So we have this addition now as the residual part. This norm is referring to something called layer norm. So layer norm is implemented by George. It's a paper that came out a while back here. And layer norm is very, very similar to batch norm. So remember back to our makemore series part 3, we implemented batch normalization. And batch normalization is to just make sure that across the batch dimension, any individual neuron had unit Gaussian distribution. So 0 mean and unit standard deviation, 1 standard deviation up. So what I did here is I'm copy pasting batch norm 1 done with the whole makemore space. And see here we can initialize, for example, this module, and we can have a batch of 32 100-dimensional vectors feeding through the batch norm. So what this does is it guarantees that when we look at just the 0th column, it's a 0 mean, 1 standard deviation. So it's normalizing every single column of this compute. Now the rows are not going to be normalized by default because we're just normalizing columns. So let's not implement layer 1. It's very complicated. We come here, we change this from 0 to 1. So we don't normalize the columns, we normalize the rows. And now we've implemented layer 1. So now the
That's fucking cool. That's tight. I like it.
For every individual example, it's 100-dimensional is normalized in this way. And because our computation now does not span across examples, we can delete all of this buffers stuff because we can always apply this operation and don't need to maintain any buffers. So we don't need the buffers. There's no distinction between training and test time. And we don't need these random buffers. We do keep gamma and beta. We don't need the momentum. We don't care if it's training or not. And this is now a winner.
So presumably we got that, right? Nice. We have layer norm. We also have batch norm. Oh, that's interesting.
It normalizes the rows instead of the columns. This here is identical to basically this here. So let's now implement layer norm in our transformer. Before I incorporate the layer norm, I just wanted to note that, as I said, very few details about the transformer have changed in the last 5 years, but this is actually something that's slightly different from the original paper. You see that the add and norm is applied after the transformation, but now it is a bit more basically common to apply the layer norm before the transformation. So there's a reshuffling of the layer norms. So this is called the pre-norm formulation, and that norm we're going to implement as well. So slight deviation from the original. Basically, we need two layer norms. Layer norm 1 is an end dot layer norm, and we tell it how many when the embedding dimension, and we need the second layer norm. And then here, the layer norms are applied immediately on x. So self dot layer norm 1 being applied on x, the self dot layer norm 2 applied on x before it goes into self dot layer norm 3. And the size of the layer norm here is 32.
So, okay.
So when the layer norm is normalizing features, it is the normalization here.
So wait. So what is... So self-attention and feed forward. So can we go back to that drawing?
It is the normalization here.
Okay, so he's sort of splitting... He's sort of getting rid of this block, and it's just... Self-attention, feed forward. Self-attention, feed forward. He's going to stack a bunch of them.
The variance are taken at 32 numbers. So the batch and the time act as batch dimensions, both of them. So this is kind of like a per token transformation that just normalizes the features and makes them unit mean, unit Gaussian at initialization. But of course, because these layer norms decided have these gamma and beta trainable parameters, the layer norm will eventually create outputs that might not be unit Gaussian, but the optimization will be. So for now, this is incorporating the layer norms, and let's train them up. Okay, so I let it run, and we see that we get down to 2.06, which is better than the previous 2.08. So a slight improvement by adding the layer norms. And I expect that they help even more if we have bigger and deeper network. One of the that is that the PDA layer here also typically has at the end of the transformer and right before the final linear layer that decodes into the vocabulary. So I added that as well. So at this stage, we actually have a pretty complete transformer from the original paper, and it's a decoder-only transformer. I'll talk about that in a second. But at this stage, the major pieces are in place, so we can try to scale this up and see how well we can push this number. Now, in order to scale up the model, I had to perform some cosmetic changes here to make it nicer. So I introduced this variable called thin layer, which just specifies how many layers of the blocks we're going to have. I created a bunch of blocks, and we have a variable with number of heads as well. I pulled out the layer norm here, and so this is identical. Now, one thing that I did briefly change is I added dropout. So dropout is something that you can add right before the residual collection back, or right before the collection back into the residual pathway. So we can drop out that as the last step here. We can drop out here at the end of the multi-head restriction as well. And we can also drop out here when we calculate the basically affinities and after the soft products, we can drop out some of those. So we can randomly prevent some of the nodes from communicating. And so dropout comes from this paper from 2014 or so. And basically it takes terminal node. And it randomly, every forward backward pass, shuts off some subset of new nodes. So randomly drops them to 0 and trains without them. And what this does effectively is, because the mask of what being dropped out is changed every single forward backward pass, it ends up kind of training an ensemble of subnetworks. And then at this time, everything is fully enabled, and kind of all of those subnetworks are merged into a single ensemble, if you want to think about it that way. So I'll read the paper to get the full detail. For now, we're just going to stay on the level of this is a regularization technique, and I added it because I'm about to scale up the model quite a bit, and I was concerned about overflow. So now when we scroll up to the top, we'll see that I changed the number of hyperparameters here about 100. So I made the batch size be much larger, around 64. I changed the block size to be 256. So previously it was just 8 characters of context. Now it is 256 characters of context to predict the 257th. I brought down the loading rate a little bit because the neural net is now much bigger, so I brought down the loading rate. The embedding dimension is about 284 and about 6 lengths. So 384 divided by 6 means that every head is 64 dimensional as a standard. And then there are going to be 6 layers of that. And the dropout will be 0.2. So every forward backward pass, 20% of all of these intermediate calculations are basically dropped to 0. And then I already trained this and I ran it. So drum roll, all of this performed. So let me scroll up here. We get a validation loss of 1.4.
Whoa! Holy cow, boy!
And this of course ran for a lot longer. This maybe trained for, I want to say, about 15 minutes on my A100 GPU. So that's a pretty good GPU. And if you don't have GPU, you're not going to do this. On a CPU, this will be, I mean, not on this on the CPU, or something like that. You have to put that like dollars and everything as well. But in about 15 minutes, we can get this kind of result. And I'm printing some of the streets here. But what I did also was I printed 10,000 characters, so a lot more when I wrote them to a file. And so here we see some of the outputs. So it's a lot more recognizable as the input text file. So the input text file, just for reference, look like this. So there's always like someone speaking in this matter. And our predictions now take on that form. Except, of course, there are the ones that when you actually need them. So it is every print to be a house. Oh, this preparation. We get you know.
That's so goddamn cool, bro.
So you can do this. It's not of course, but this is just a transformer train on the character level for 1 million characters. So it sort of like blackers on a Shakespeare-like manner, but it doesn't, of course, make sense at this scale. But I think still a pretty good demonstration of what's possible. So now, I think that kind of like concludes the learning section of this video. We basically kind of did a pretty good job in implementing this transformer, but the picture doesn't exactly match up to what we've done. So let's go on with all these additional parts here. So let me finish explaining this architecture and why it looks so fun. Basically what's happening here is, what we implemented here is a decoder-only transformer. So there's no component here. This part is called encoder, and there's no cross-attention block here. Our block only has a self-attention and the feed forward. So it's missing this third in between piece here. This piece has cross-attention. So we don't have it, and we don't have the encoder, we just have the decoder. And the reason we have a decoder only is because we are just generating text, and it's unconditioned. We're just blabbering on according to a given data set. What makes it a decoder is that we are using a triangular mask in our transformer. So it has this autoregressive property, but we can just go and sample it. So the fact that it's using triangular mask to mask calculation makes it a decoder, and it can be used for other stuff. Now, the reason that the original paper had an encoder-decoder architecture is because it is a machine translation paper. So it is concerned with a different setup. In particular, it expects some tokens that encode sacred.
Oh. Okay.
So you typically, these here are special tokens. So you are expected to read in this condition on it, and then you start off the generation with a special token called start. So this is a special new token that you introduce, and always place at the beginning. And then the network is expected to output neural network.
Genio.
So this part here will be decoded exactly as we've done. Neural networks are awesome. Will be identical to what we do. But unlike what we do, they want to condition the generation on some additional information. And in that case, this additional information is the French sentence that they should be translating. So what they do now is they bring the encoder. Now the encoder reads this part here. So we're only going to take the part of French, and we're going to create tokens from it, exactly as we've seen in our video. And we're going to put a transformer on it. But there's going to be no triangular maps, and so all the tokens are allowed to talk to each other as much as they want. And they're just encoding whatever's the content of this French sentence. Once they've encoded it, they basically come out from the top here. And then what happens here is in our decoder, which does the language model, there's an additional connection here to the outputs of the input.
But what is the loss function? I don't get what the loss function is now.
The keys and the values are coming from the top, generated by the node inside the decoder. Okay? And those plots, the keys and the values there, the top of it, feed in on the side into every single block of the decoder. And so that's why there's an additional process function. And really what it's doing is it's conditioning the decoding, not just on the past of this current decoding, but also on having seen the fully encoded French product. Sorry. And so it's an encoder decoder model, which is why we have those two transformers and conditioning log and so on. So we did not do this because we have nothing to encode, there's no conditioning, we just have a text file, we just want to imitate it, and that's why we're using a decoder only transformer, exactly as done in GPT. Okay, so now I wanted to do a very brief walkthrough of all GPT, which you can find on my GitHub. And then we can basically two files of interest. There's train.py and model.py. Train.py is all the boilerplate code for training the network. It is basically all the stuff that we had here as the training. It's just that it's a lot more complicated because we are saving and loading checkpoints and pre-trained weights, and we are decaying the learning rate and compiling the model using distributed training across multiple nodes for GPUs. So the training.py gets a little bit more very complicated. There's more options, etc. But the model.py should look very, very similar to what we've done here. In fact, the model is almost identical. So first, here we have the causal self-adjustment block. And all of this should look very, very recognizable to you. We're producing queries to these values, we're doing dot products, we're masking, applying softmax, optionally dropping out, and here we are pulling the values. What is different here is that in our code, I have separated out the multi-head notation into just a single individual head. And then here, I have multiple heads and I explicitly concatenate. Whereas here, all of it is implemented in a batched manner inside a single column self-attention.
Yeah, see how they have an extra dimension here? So this is B by N head by T by heads. Or N head, or whatever you... Or we're not N head. What did he call it? Whatever.
We also end up in a fourth dimension, which is the heads. And so it just gets a lot more so hairy because we have four-dimensional tensors now, but it is equivalent of now. So the exact same thing is happening as we have. It's just more efficient because all the heads are now treated as a batch dimension as well. Then we can look at perceptron. It's using Regalian nonlinearity, which is defined here instead of running. And this is done just because OpenAI used it, and I want to be able to number checkpoints. The blocks of the transformer are identical to communicate with base and stuff, and then the GPT will be identical. So the block the transformer are identical to communicate with base and stuff, and then the GPT will be identical. We have the position encodings, token encodings, the blocks, the layer one at the end, the final linear layer, and this should look all very recognizable. And there's a bit more here because I'm loading checkpoints and stuff like that. I'm separating out the parameters into those that should be weight retained and those that shouldn't. But the generate function should also be very, very simple. So a few details are different, but you should definitely be able to look at this file and be able to understand what this is now. So let's now bring things back to ChatGPT. What would it look like if we wanted to train ChatGPT on this, and how does it relate to what we learned today? Well, to train ChatGPT, there are roughly two stages. First is the pre-training stage, and then the fine-tuning stage. In the pre-training stage, we are training on a large chunk of internet and just trying to get a first decoder-only transformer to babble text. So it's very, very similar to what we've done ourselves, except we've done like a tiny little baby pre-training step. And so in our case, this is how you print a number of parameters. I printed it and it's about 10 million. So this transformer that I created here to create Shakespeare transformer was about 10 million parameters. Our data set is roughly 1 million characters, so roughly 1 million tokens. But you have to remember that OpenAI is a different vocabulary. They're not on the character level. They use these subword chunks of words. And so they have a vocabulary of 50,000 roughly elements. And so their sequences are a bit more condensed. So our data set, the Shakespeare data set, will be probably around 300,000 tokens in the OpenAI vocabulary, roughly. So we trained about 10 million parameter model in roughly 300,000 tokens. And when you look at the GPT-3 paper, and you look at the transformers that they trained a number of transformers of different sizes, but the biggest transformer here has about 75 billion parameters. So ours is again 10 million. They use this number of layers in the transformer. This is the n embed. This is the number of heads, and this is the head size, and then this is the batch size. So ours was 65, and learning rate is zero. Now when they train this transformer, they trained on 300 billion tokens. So again, remember ours is about 300,000. So this is about a million fold increase, and this number would not be even that low by today's standards. You'd be going up 1 trillion and above. So they are training a significantly larger model on a good chunk of the internet. and that is the pre-training stage. But otherwise, these hyperparameters should be fairly recognizable to you, and the architecture is actually like nearly identical to what we would get ourselves. But of course, it's a massive infrastructure challenge to train this. You're talking about typically thousands of GPUs having to talk to each other to train models of systems. So that's just the pre-training stage. Now, after you complete the pre-training stage, you don't get something that responds to your questions with answers and it's not helpful and etc. You get a document repeater, right? So it babbles, but it doesn't babble Shakespeare, it babbles internet. It will create arbitrary news articles and documents, and it will try to complete documents because that's what it's trained for. It's trying to complete the sequence. So when you give it a question, it will just potentially just give you more questions. It will follow with more questions. It will do whatever it looks like some closed document will do in the internet. And so you're really kind of like undefined behavior. It might basically answer the question with other questions. It might ignore your question. It might just try to complete some news article. It's totally on the naughty, as we say. So the second fine-tuning stage is to actually align it to be an assistant. And this is the second stage. And so this ChatGPT blog post for OpenAI talks a little bit about how this stage is achieved. We basically, there's roughly 3 steps to this stage. So what we do here is they start to collect training data that looks specifically like a writing system would do. So we have documents that have the format where the question is on top and then the answer is below. And they have a large number of these, but probably not in the order of the internet. This is probably in the order of maybe thousands of examples. And so they then fine-tune the model to basically only focus on documents that look like that. And so you're trying to slowly align it. So it's going to expect the question at the top and it's going to expect to complete the answer. And these very, very large models are very sample efficient during their fine-tuning. So this actually somewhat works. But that's just step 1. That's just fine-tuning. So then we actually have more steps where, okay, the second step is you let the model respond, and then different raters look at the different responses and rank them for their preferences to which one is better than the other. They use that to train a reward model. So they can predict, basically using a different network, how much of any candidate response would be desired. And then once they have a reward model, they run PPO, which is a form of policy gradient reinforcement learning optimizer, to fine-tune this sampling policy. So that the answers that ChatGPT now generates are expected to score a high reward according to the reward model. And so basically there's a whole aligning stage here, or fine-tuning stage. It's got multiple steps in between there as well. And it takes the model to a question answerer. And that's not a whole separate stage. A lot of this data is not available publicly. It is internal to OpenAI, and it's much harder to replicate this stage. And so that's roughly what we do with ChatGPT. And ManaGPT focuses on the pre-training stage. Okay, and that's everything that I wanted to cover today. So we trained, to summarize, a decoder-only transformer following this famous paper, 10 years on need, 2.7. And so that's basically a GPT. We trained it on tiny Shakespeare.
All right, so maybe we should
all the training code is roughly 200 lines. I will be releasing this code base. So also comes with all the GitLog commits along the way to be built up. In addition to this code, I'm going to release.
Dude, he just released his email, bro. You could just email Andrzej Karpathy, bro. I feel like he's gotta he can't be using that anymore, bro. He just leaked his email. That's crazy, bro. I've never typed git log in my fucking hell no, bro. Yeah, okay, so I was thinking of doing this, gpus.com. I made an account. So he said A100, right? Pricing. On-demand one. Yeah, so they just have pre-sized things. What is this? vCPUs? I don't know why you need so many CPUs, but RAM, that's gotta be VRAM or no? Oh no, this is VRAM per GPU. You have 40 gigs. So wait. Okay, in any case, let's start to do the data gathering. So I already have GitHub on and video transcripts. And I have some code. We're going to restart this. We're going to do this over again. I should have just ignored this. I should have just gotten rid of this. We're going to do this again. Okay, so Okay, so let's just so we're just gonna get our data. So first off, do we even have YouTube DLP? Whoa. Why don't I just use pip? So I feel like this is really weird though. I don't even remember doing this, but this is very weird. I don't want to clone it though, and I don't know why I don't want to clone it. Where's my source code? What did I use Python for? Oh, tokenization. Yeah, we don't need to tokenize that because what we're gonna do is we're gonna do words. We're gonna do words. I mean, we're gonna train on characters anyways. I'm not doing fucking, well, let's see. So we're done with this. What's new in this one? When was that?
So today we are going to be continuing our Zero to Hero series.
Dude, Andre's just so sick, man.
24 million version of it. So when OpenAI released GPT-2, this was 2019, and they released it with this blog post. On top of that, they released this paper, and on top of that, they released this code from GitHub. So OpenAI/GPT-2. Now, when we talk about reproducing GPT-2, we have to be careful because, in particular, in this video, we're going to be reproducing the 124 million parameter. So the thing to realize is that there's always a mini-series when these releases are made. So there are the GPT-2 mini-series made up of models at different sizes, and usually the biggest model is called the GPT-2. But basically, the reason we do that is because you can put the model sizes on the x-axis, plots like this, and on the y-axis, you put a lot of downstream metrics that you're interested in, like translation, summarization, question answering, and so on. And you can chart out these scaling laws. So basically, to spin up these kinds of boxes, by the way, my favorite place to go to is Lambda Labs. They do sponsor my development and that of my projects, but this is my favorite place to go, and this is where you can spin up one of these movies.
Bro, sick.
So I like to spin them up and then
Okay, so anyways, what we're doing, let's just do this. Okay, so let's think about what this project is as a version 2. So what we're gonna do is we're gonna get it all into Julia, just because. Okay, so we could leave this in here. But we do want to let's just fucking let's just see if this works. So this is my channel ID. So presumably we can interpolate into this. Okay. This is going to be what is the other one? Shorts. Strings. Okay. So this is going to be $T. This is going to be $T. Oh wait. And but I think do we even want to do this? Can we try this? Let's just try this. I don't know if it's gonna find the binary. I guess we'll find out. But, well, let's just see, because I just installed it. It might not be even on the path. No, we think we're good. Special commands. Or special hash. What's at run? But can't we do read command to string? Because then we could just write lines. So then we can get rid of this. So wait, so first off, I just get this. Oops. Wait. Can we go back? Because this... So just say T is equal to... Let's just do shorts because they'll probably be the quickest. So let's do this. So if I go here, it's going to open Chrome, unfortunately. Okay, good. So that works. So now we just need to try to do this. So what did it say? I hate this. This is so stupid. Must be quoted. Okay, so I need to just quote it. Okay, so let's just do this. It's IDs, dollar, URL. And then this needs to be backslash, backslash. And then what else is there? Is that it? I think this works. No, what? Wait, so wait, hold on. Okay. Wait, yeah, what? Read command to string. The hell is that? Let's just fucking. I feel like there's no freaking way it's gonna work. So it didn't escape it. This is errors, right? Let's just see if I can fix it. I haven't done this in a while, just mindlessly fucking. Oh, nice. That's fantastic. So can I just do... Wait, it went to my video? Okay, but that was fast, so that's good. Nice. Okay, cool. So I don't know. I guess it fixed something. All right, so we got the command, we got the URL. We're gonna take this in here, dollar URL. Okay. This is the command, and then we're gonna run pipeline standard out equals a file, and this is going to be $t. Okay, and this is actually going to be this dir, and then it's gonna be data IDs. And what's wrong with this? I think, oh, it's just this. All right. Nice. Um, wait, what? Why doesn't this work? What is this doing? Control Shift select to end. Whatever. Join. Let's do what I want. No. Join is such a weird ass thing. I want to do a cat. What? Stack? Dude, what the fuck? How to join a vec of strings? No, that's fucking stupid as hell. What? Oh my god. Holy hell, DuckDuckGo fucking sucks. Um, Yeah, you do reduce a VCAT. It's such a fucked up thing. Okay. So what's the next thing? We just want to get the transcripts, right? So we're gonna make a directory in here called transcripts. Okay. Why is there a breakpoint there? Okay, so now we need to just do this, right? I mean, this is I mean, whatever. I don't give a shit. Oh, we need to do. Okay, and we got all of them. All right. So now we need to Now we need to get the transcripts. So we just need to run. Of oh oh XD. In any case. Wait, what? So I think we just have to run it, right? And what does this do? I think we just need to run grab. But the thing is, I kind of want it to show, right? That was the kind of nice thing about this thing. I don't know. I don't know how you get. This needs to be, wait, but we need to figure out where it writes to, right? I think I could just do dash P. Okay. Let's try it. Let's try it with like the shorts URLs. So this is going to be This is going to be dash p data transcripts. Okay, cool. But why is it also doing the VTT? Wait, this is... Wait. I think I fucked this up. Oh yeah, I did fuck this up. Okay, that's okay. We can cancel this. So the JSON's good. We just... I never pushed my changes, and I feel like it might have been on the other computer. What? Oh, that's the real command. I'm such a dumbass. Okay, so let's just start by getting um let's just get the video metadata. So first off, let's just take this fucking okay. Let's run this. Okay. So now we want to run we want to run we want to run write info JSON skip download -a -p data metadata. All right, that's all we. And then this needs to be IDs, and you data IDs. And is it all IDs or is it just IDs? Just IDs. All right, so I'm pretty sure we can just do this. Okay, and then now we do want to copy over some of this code that I wrote. So let's just duplicate this. Oops. So we can just do, and then we'll activate it. So this is going to take a long time. But the advantage of doing it in two parts is that, and the problem is this stuff is such bullshit. The stuff that you actually care about is like what the hell is all this? I mean, it's actually insane how this thing is designed. Like, it's clearly like a bunch of engineers just kept having to add more and more shit to this. They're like, fuck it. We're just going to put every language in here. Insanity. There's all just about subtitles. There's like 99.9% of this whole metadata thing is just about subtitles. It's totally crazy. Is there like a views thing? View count. There you go. What the hell is this? It's thumbnails. Thumbnails. Totally insane, man. Duration. What are all these durations? What is this? Whoa. It like has like screenshot arrays like over time. That's weird. Storyboard. There's so much random shit in here, bro. Ooh. We don't have FFmpeg on here? How do you get FFmpeg? Dude, it's such a joke. FFmpeg is better than OpenCV, but it's also just like, why aren't these like critical? There we go. It's just a download. Yeah. Yeah, I would love if you could just give me. It's like I don't understand why they don't provide Windows builds. Oh, here we go. Winget install FFmpeg. Winget is the way I like to do things, honestly. But then I don't know if it actually adds it to my path. I think I still have to add it to my path. So silly. This thing takes forever. Oh gosh. These date ones. Anyway, so basically what we're gonna do is we're gonna find the important set of fields. So automatic captions, just hide that. Hide that whole thing. There we go. Now it's starting to look a little bit normal. I don't care about any of that. I don't care about the... Oh, the tags. Maybe we'll do the tags. View count, age limit, web page URL, categories. I feel like maybe I just want... This was a while ago. Not that far away. Thumbnail, thumbnail. Wait, wait. Well, what is that artist? What is that artist? Thumbnail, Alright, I don't want to get a freaking strike. Oh, thank God that didn't do something ridiculous, like overwrite the file, rename it. Okay, so let's just read one of these. Let's just get started. Okay. function get IDs. CID. Boom. Left. Cool. So now it should not be a bunch of malarkey when I run this whole script. Okay. So the next thing is oh, we also want to know stuff about like when it. Okay, let's do this locking in one. Copy path. All right. J example is equal to this. I'm gonna take this and this. Fucking god, bro. Is that the last one? Let's change them to the slashes. Okay. I guess there's a weird non. All right, let's just say read. Oh wait. I think I probably have this, but whatever. Okay, so does that work? Okay, great. So the fields. Wait. So how does JSON tables work? Because let's just take two of these. Let's take another one. Pitch assembly. Copy path. Okay. JX2 is equal to this. Take this. Do. Okay. Okay, then data frame. Oh yeah, we need to do. I don't know how long this is gonna take, but this is my classic data science package set. JSON, CSV, data frame. I spent so much of my life just fucking with this bullshit. So I'm pretty sure this just works, right? What happened? Key release timestamp not found. Wait, what was this? Pitch assembly. So this is the one. Git head. Oh no. That's that's stuff that YouTube DLP added on. That's funny. That's silly. Okay, but so then let's go to the other one. See, oh, jeez. Wait, pitch assembly. Wait, exam 2 review was live. So I don't know, is there another timestamp? Okay, so there's this. And there's this. What is that in milliseconds? Is that epoch? $11.14. Okay. That was the okay. That's interesting. Oh yeah, so I've been wanting to do statistics on this for a long time actually. So we do need to know comment counts, channel follower count. Okay, so I think in stats we had a thing. Okay, let's just parse segment, parse event, get timestamp words, get text transcript, get event transcript, Token tally. Get video ID. I feel like this works now, right? I feel like I fixed it. Get video ID. So what is S? Oh. That's goofy as fuck. Okay. But now we want to find... Yeah, this is what we do. FN's 2. Okay, but we don't want the transcript, we want the metas. Okay, so let's just hop back in here. So yeah, so this throws where J and J2, one is video, other is stream, release timestamp here. Okay. So we got this. So FNs, so let's just make this right. So MFNs, let's see, are we done? We're done. This content isn't available. What is that? That must be this one. Because we got this. Well, I don't know. Let's just go to the video ID. So, wait, where were we? So, we're here. I'm going to go like this. What is this? Couldn't find this? I remember this. Why couldn't he get this? I wonder what happened. So, it's kind of annoying because I guess I'm missing some. So, we should know... So, I guess we want to know... Okay, alright, okay. So, I mean, a bunch of this is just data science stuff that could be totally automated, but let's just reader data metadata join equals true. So we have this. Do we have that function get video ID? Well, first off, do we have IDs? We have IDs, right? Okay. So get video ID, where's that function? Can we get the fucking JSON thing up here? So get video ID. Just put this up here. That stuff is old, bro. We got this. Get video ID. Okay, so we got the... Okay. So this is not the... These are the M's. Oh, shit. Wait, hold on. So we got this. And then this. This is... Oh, this is only missing one. Huh. Okay, so let's just do that. What are the M's? The M's are going to be JSON3.read. And let's do the at dot. And we're going to do J is equal to that. Or J's. M's. Let's do M's. It's going to take fucking forever. Let's just do for right now so we don't have to reread it. M's equals J. It's absurd. Dude, I remember, it's like, it's insane. Okay, so we got this. And we can just delete that. So now we got, this. We got this. Okay. So now we have a dict of that. But what we really want is, okay, wait, we want to read all the video IDs. So let's just get all the video IDs. So vids is equal to, or vid IDs is vidids is equal to read uh read lines of IDT function of video. Okay, great. So now what we want is get the dtxt's vid IDs. It's insane that that's not part of the standard lib. Okay, so then vidjs is this. And then we want to do data frame of vidjs and see if that works. It's slow because of this. License not found. Okay, so what if we just do uh field names dot vidjs. What is it not field names? Can I just do keys? Intersect. Okay, great. So we got this. Okay. And it's probably missing all of the good stuff. I'm sure it is. So let's print this. Was live, live status, automatic captions, full title, upload date, format, audio extension width, resolution, like count. View count. It's got view count. It's got the dates. Unfortunately, I'm missing some, but that's okay. So then we're going to do map. So, okay, so we're going to take. So we're going to say these keys. So I wonder if we can. Okay, so these are Ks. So then we want to say we got vidjs, right? Vidjs. So it's just say J is vidjs1. Okay, then we want to do get the J Ks. Map is not defined on sets. Ay, ay, ay. So stupid, bro. All right, cool. So we got. Wait, no, but that's not what we want, though. We want. So wait. So I guess we do. Here's. This doesn't work though, right? Does this work? Oh, how do you filter keys out? Can I just delete? Okay, so what we want is keys of J, set diff, those keys with these keys. So it doesn't have license and it doesn't have file size. So let's just say these are bad Ks. And then we do bad delete bad Ks1. Oh fuck. Wow. Sets are so poorly supported, bro. Oh. Ay ay ay. Ay Dios mío. I really have to let's ask ChatGPT. It's not gonna know though. I have a bunch of JSON3 dot objects. Is that what they are? At type. But the problem is that the keys are somewhat distinct somewhere. So I took the intersection of all of the keys that are in all of them, and I was gonna filter, but I don't know how to filter the JSON object to just delete or remove or basically make it so that the problematic keys aren't there. But I don't know how to do that. Oh yeah, could we just do that? Wait, why don't we just do that? I feel like that might work. Okay, so is there a 1R get D? Let's just say x to x vidjess. What the fuck is that? Okay. D's. Oh yeah, yeah. What the fuck? Bro, what? Let me just do this. Why don't I do this? Number of columns and number of column name. Wait, what? Wait. Uh, dude, it's so fucking stupid, bro. Let's just do this. Um, oh my fucking god, bro. Why does it always do the wrong thing? It's so literally so stupid. Holy fuck, why would it think that that is what I want? Okay. I'm pretty sure this might help out. Okay. Oh, obviously it didn't work. Okay. Yeah, see, this doesn't do what the fuck, which is great. That's great. So, um, how do you get around this? Okay, what is the type of D? D. Vector or vector of any. Right. What if I just reduce VCAT on this? Wait, or VCAT? Is that a matrix? Okay, great. It's a 66 by, okay, so let's just do this. Data frame X prime. That's what I want. That's what I want. So yeah, obviously they don't want to do it just for me. Now I provide the names. What? Collect adjoint of a. Oh, you've got to be kidding me, bro. I've run into all of these things 1,000 times, and it's so fucking stupid. I think you have to do permute dims. There we go. Finally. Okay, there we go. Finally. Let's just see if we csv.reddit. Uh, why did it fail? Because of these stupid fucking captions? That's great. Okay. So wait, so let's just get the names of the what do we actually want? And of course it doesn't print them out. Alright, so we want like count categories title. It's still gonna fucking yell at me. Anyways, channel uploader URL. I guess we could do URL. Format ID, uploader URL, resolution type, ID. That's of course, we want that one to be like up there. We want the view count. Oh yeah, duration. Timestamp. What is timestamp? Okay, we want duration. A description. We need a description. So, ID, title, view count, duration. Ooh, availability. Can we look at that? Is that in this? That's a video. Let's see. This is a video. Oops. Public. Okay. They should all be public. Okay. Oh, wrong one. Okay, so we don't need that. Quality. Why don't we get what's quality? Quality 6.0. It's a weird field. I don't know what the fuck that means. They all have file size approx. I'm down to put that in. Display ID, age limit, epoch. I don't know what epoch is. We definitely want duration. What's subtitles? Subtitles might be the long one. You know, timestamp. Okay, so now we just want to take those and go like this. Okay, so now we want to do df, and we want to get a bunch of columns. So I think we want... There we go. Nice. Unfortunately, we don't have watch time because it's not public information, which is insane. Duration is just in seconds. What is this? Do we have the URL? What is this URL? Well, I guess it omitted it. Let's just take this. So wait, let's just sort by the duration. Okay, so let's make D this. So D. So I do want to get all of the So what the hell? Oh, this must just be one of those really old ones, but it's probably like. Well, what is that? That's 18. Fuck. Like 5 hours. That's not even close to the longest one. The longest stream. Was this. Got 1 like. Let's sort by taking pictures. Damn, the one after that's got nothing on it. And I always put it as gaming, bro. Why did I put it as gaming? I think that was just you know what I think it was? I actually have no idea why I don't know. Honestly don't know. Let's see if we do this and I do D again. Why doesn't it fill all the way to there? Whatever. Oh, is this all of them actually? I guess it's all of them. Alright, so let's sum the duration. This is just the videos though. What? So stupid. This is one of those things where it's just like it's just so much worse than so this is 33 days. Okay, so but what we want to do now is uh let's this fails. So why don't we do this? Oh. Wait, what? Oh, this is gonna be such a pain in my ass. Why did we do this? We should have done. It's 330. We should be fine. DTXTs. SIDs. Oh, because uh can you do this? Can you do this? Yeah, I don't think you can do that. Whatever. S keys, SJs. What do we get? 54 in here, way less. Let's print them. Yeah, I want to know. Okay, I want to. So, can we figure out how do we do this? Is this really what happened? I mean, this is just such a fucking crazy thing. Okay, so we got SDS map get keys. K is gonna be SKs, and this is gonna be SJS. We had these, and then total malarkey, and this is gonna be SDS, and the header is going to be SKs, and this is gonna be SDF. Okay, fantastic. So wait, do we have all of the good ones though? The SDF blank. So we're missing duration. What the fuck? This was live, right? No, wait. Pitch assembly. That might not have been live. Let's get a channel URL, webpage URL. Fucking god. Here's a. Okay, so let's find this in the file names. How do we search for file names? What? How do I toggle whether or not it? Um, stupid. There we go. Training AI on my own transcripts. Oh, but that's right now. Fuck. Fuck. Obviously, I picked the first one. I'm such a dunce. Okay, so this. Let's see. So wait, so why doesn't it have duration? You know what it is? I think it's just that the current one doesn't have duration. I'm almost positive it's that. Okay, so let's so why don't we wait, so did it fail or it failed to get those keys because it doesn't exist in them? What did I actually do? But it just doesn't have that column. But that's because what if we just did these SJs? What if we just did 2 to end here? Did it give me more? I don't know which one's which. Fuck. Oh, you know why though? It's because of these fucking keys. Okay. Fuck. Bro, what? URL not found? Why do I even need URL? I don't even need URL. Let's do it again. There we go. I mean, what is the point of URL? So we've done 66. Okay. It's I don't know. It's- yeah, the Berkeley shit went pop the hell off, dude. The thing is, none of this is by watch time, and it's so stupid. It's hard. It's easier to scrape than it is to. Anyway, so we'll get the transcripts the next time, I guess. Should I just get the transcripts right now? I mean, I have hella data. Let's just do it. So what is the command though? We need to figure out the command. The command is this. Wait, which one is it? Is it sublang n or is it right auto set? Okay, let's fucking try this. Okay, so now we want to put this in here. So this is gonna be subformat JSON 3, write auto subs, which I think might fuck me, but so we're gonna do -p data transcripts. And this is just gonna be urls.txt data IDs. Oh, IDs. Oh wait, hold on. Can I just give it IDs? I might be able to just give it IDs. Right? Hopefully. So let's run this shit. Okay, so let's look. Wait, where the fuck is it putting it? There we go. Okay, nice. So we're getting them all. These things are huge, actually. They're really big files. But now we'll have our data set. I just like how structured it is, but it's obviously like the most inefficient way you could possibly store. I don't know. I don't know, man. It would be nice to make this a little clap tool. The thing that I want more though is I want to use this cool thing that I know about called DLM, Rust. This thing is so fucking good, bro. I mean, it's actually so good. You give it a text file and it just slams whatever it is. I remember I downloaded like the entirety of the Wolfram documentation in like a second. I mean, it was so fucking good, and the tool, it's just one of those nice tools that no one else has seemed to have done really well. I love DLM, bro. Who is this guy again? I forgot, bro. He's so sick. Quadrant vector search. He's kind of an AI guy then. Dude, but he's all Rust every day, dude. What a fucking hype guy. No way. That's awesome. Whoa. That's like really good. That's awesome. All right, so we're gonna wait around a little bit. Then I do want to compile. I want to take a look at this data again. I don't know how long this is gonna take, but we're getting to the point where I sort of understand this multi-head attention shit. I mean, it's like I don't know. It's like there's no magic. It's just a bunch of matmul. Like, is it really that special? I don't know. Let's do a get in it. Let's start to why is that there? What did this? What is this? Let's ignore them. Do 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 do. It is so slow. Because it's clearly not multi-threaded. I don't know if that's because they there's like an unwritten agreement or something that like YouTube's like, all right, we'll let you guys do it, but you can't hammer us. I could see that being a thing, a rate limit. Because they'll be able to tell. They put YouTube DLP in the user agent anyways, so it's like you're not getting anything by them. I like that, and I don't understand it, but it uses a different slash. What is this ASCII character? Oh wait, is this gonna close it? Okay. It's like big slash. Wait, why don't I just use Julia? Big Solidus. Ha! So I call your mama Big Solidus, bruh. Uh, got it. So I do want to make this searchable. It would be cool if I like, I don't know. I mean, it's searchable right now. The problem is it's get ignored, so I guess I have to do find in and then it'll work. I like that you see these little diatribes here. You know, the date ones. I like that it does a renaming, bro. That's so funny, but it's like, that's great. I'm so glad they did that. I know it means that it's not the identical character set as the title, which is a little bit weird, but we'll just know to replace the character back with a normal slash after the fact. But then at least it doesn't make some random directory structure in my freaking... That'd be such a pain to deal with. Oh. Thank you for applying to UC Merced. Are we done yet? Oh, look at all these failures. We definitely need to know... I mean, the thing is, I kind of want to know also... That doesn't have transcripts on it? Yeah, it does. So what does that mean for a... Oh, that's terrible, man. What the hell? Wait, what are the error messages? This content isn't available. This content isn't... This is the ZNW... Alright, so this is this one. But I have no idea why. I mean, how many failed? We have 330 total, right? Haha. Haha. Funny. Why doesn't this have captions? See, that's the problem with this because that's what I ran, right? But Rick roll. Um all right, look, I don't care. I honestly don't care. So what we need to do right now, we need to just run through some of these functions and see. You put this in a package or something. Parse segment, parse event, form F, la 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 la. I'm gonna put this down. Okay, let's just fucking do this. We're gonna take this. It's here. I'm gonna copy this. Oh, whoa! 177? See, that's crazy because is it gonna tell me how many files are in the old one? Let's see. This is the right thing? Maybe that is 177. But why is there so few? I feel like alright, like let's go through this. I mean, look how many it's missing. What the hell? Oh yeah, bro. And it's clearly not because of an old new thing, but that stinks. Alright, well whatever. So what did we want to do? What did we do? Okay, you read all these JSONs. Alright, so we're gonna get these J's. Then you get the DIRs. No, yeah, this is clearly not gonna work. Oh, F, what does F do? Duration? Oh, that's just to get the duration. FN's 2. Okay, read these. J, read this. That's an example. E, okay, we can do this. J equals J is 1. Okay. Tally has key dot. Okay, that doesn't work. Get segs. Let's see. How does that do it? Oh. So what is that? Oh, nice. What video is this from? Oh, wait, we don't even, um, oh, that's unfortunate because we need to, oh yeah, we do need to zip the, where was that zip thing? IDs, FNs too. Yeah, right, so we need this. So let's just do this. This is FNs. Okay, great. So So J's. Wait, we don't want this, do we? IDs to T's. Let's see. I don't know what this is from, but let me just do this. Can we... What is this from? Wait, this is the first one, right? So this should be IDs 1. Okay. Training an AI on my own self. Okay, so wait, so we sort of have... But the thing is, this output is Garbo, bro. So it's like... First off, is this even right? Okay, so we got the FNs. Okay. Okay, so we get the... And then we get the IDs. Okay. Then we get the J's. Then we get the first J. I don't know what this is. Then we get the transcripts, and then we get this, and then we get the DTXTs. So what? Okay, wait. I just want to do some basically more frequency analysis. I know I've already sort of done this, but we did it with yeah. So we get the join. Oh wait. Oh yeah. We need to do. So this is apparently the whole data set. Reference planes. No, wait. It's dude. That's so messed up. Watch. They don't shitty. They don't block out, but wait, why can't I? Um, dude, they block out. Fuck, the most disgusting shit. What is that? I don't think I said that. What is this garbage? What the fuck am I reading? I guess it did it read it alphabetically because these are like not chronologically sorted at all. This is crazy to look at a timeline of my whole freaking life, dude. And it's all bullshit. It's all bullshit. All right, so let's delete. Let's just move this to here. Wait, not there. Fuck. What? There we go. Okay, so that's ignored. What is this? All right. I mean, but that is what we're gonna be. I mean, that's one of the things about this LLM stuff that's so cool is you could take any string and just start to fucking learn on it. So it's pretty cool. How big is that file? It sucks how many we're failing, dude. We have got to figure that out. I'm thinking maybe I give up on the timestamp thing a little bit, and then I download the VTTs because I'm guessing if I download the VTTs, I'll get or this whatever they're called, I'll get a way higher percentage. I think it's just the right auto sub feature. So let's this is gonna be did it work? All right, cool. So solid little 5-hour stream. We're we're getting close to implementing a freaking neural network, and hopefully we'll be able to use the GPU. I'm gonna look into using Lambda. I think that'd be fun. I don't know if I'm gonna be able to do that on stream, so I'll probably have to do a dry run, see if that works. Anyways, pretty good. Not the worst stream. I mean, why don't we just try to run? Okay, so we just take food out text. We copy this path. But then, okay, but then that's the thing though, is like this is so big that you can't just build the training set. You have to just generate a random index and then make it on the fly, because otherwise you're gonna fill your RAM. But also, it's like this thing is not going to be. I don't know. His bigram model was like a little bit more surprising than I thought. All right, can we just read this and do a word frequency thing? So okay, so we got this. So this is S. So can we give it multiple things to split on? Oh wait, I think we could just do split S. To the confined. Well, now I'm saying confined, 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 confined. It's no longer the bottom. Suck that, fuckhead. All right, so let's look at this again. These are the words, not the tokens. To the I, this, so, is, that, we, it, and a. Okay. I say okay all the time. You just do of like what it's going. Oh, yeah. But in right B, that's wait. Yeah, I say wait all the time too. Then want have for. Where's the curse word? There's the curse word. Oh my god, bro. I've cursed 3,000 times on stream and I'll fucking keep doing it. That's funny. It's interesting just how much of my vocabulary is like com- just complete garbage. I don't think there's. I mean, we could take this tally and do a simple bigram word model, right? How hard would that be? You tally the pairs and then you sample. So that would be fun. I would like to see a bigram word model. Let's see. So what was this? This is some of the batch norm stuff. Oh no, no, this is like looking at the math of attention. Starting self attention. I think I'm gonna go just read my book. I don't feel like I want to get started on the next step yet. Soon it'll be really cool though. See it really generating. I kind of want to be done with this because it's like I kind of just want to be able to say that I've trained an LLM, which is like in some way a bad way reason to do it, but I am curious about how it works and I feel like I'll know more as I get through it cuz like so far this multi-layer this MLP version I just feel like it's such a toy that I don't even get everything I want out of this. So I mean, it's like I don't know. It's like such a simple setup that it's like all right, well, I mean, I feel like I'm good.